anything else, I'll get the slideshow set up from current slide. But let me go over these two announcements. There may be more, but these are the only two I know about right now. Coming up in a couple of weeks, February the 12th on the Birmingham West campus, from 9:30 to 10:30, 11:30 in the morning, there will be the Lawson College Transfer Fair Days, and this will be in the academic building, which is B Hall, and that's going to be, there'll be tables all up and down the hall for all these schools will be there, and the whole list is here. You are welcome to come look at it and see who have been invited to come. No guarantee they'll be here. That's Wednesday, February 12th, 9:30 to 11:30, and then the next day, Thursday, February 13th, they'll be here on this campus in this building. I believe it'll be down in the faculty dining room, which is right next to the cafeteria. They say the campus cafeteria in Building A. I think it's right next door to that. Okay? And again, all these schools have been invited to be there. Now, for those of you who may be interested in a summer research opportunity for engineering students, they have one going on at University of Illinois, University of Arkansas, and Howard University. 10-week internship. They pay you $5,000 to go and learn a lot. Okay, you don't pay for it; they pay you to. They also house you free for that 10 weeks, huh? And with the housing comes a meal ticket, so they feed you for those 10 weeks, and they also pay your airfare there and back once.
Now, what you have to have?
You can read this and see. Okay. It's mostly geared for engineering students in areas of mechanical, electrical, and material engineering. But you also, it's an incredible learning experience. The deadline for it is February the 15th. And the title of it is POETS. It's the Power Optimization of Electrothermal Systems. POETS. Okay. Yes?
Do you have one in my field of expertise?
What is your field of expertise?
Do you have $1,000?
There may be. I don't know of one, but you can check it out. Yeah. Check it for Student Financial Services. They have lots of information on things like this. Okay. Yeah. Now, let me make sure I've got everybody here. Did anyone not hear your name called when? Okay. Yeah. Yeah, but remind me.
Davis.
Huh?
Jerome Davis.
Yeah, Jerome. Okay. I thought you had been here.
Yeah.
Okay. And I think that's the only one, right? No, you came in. Brandis. Okay. All right. Anybody else? Okay. All right. Now for Bridget's purpose, and we go over what we're doing. So right now, everything that. Whoa. I thought this was recorded. Yeah, it is. Okay, I can't see it here. It is recording. If you see this, it's recording. I couldn't see that in the bright glaze of the sun, glare of the sun. So, are you familiar with Blackboard? Okay. This new Blackboard or the old Blackboard? This term we've gone to a new Blackboard. And I think for student purposes, it's not that hard to navigate, is it? Okay, but if you go to this class in Blackboard, you'll see the first thing listed there is the syllabus. It's up to date. It should be there. The next thing is my locator card. That's when I'm in class, out of class, on campus, off campus, and what classes I'm in and what times, and on which campus. Okay. The next thing is the research paper instructions, and they're there. The next one is, I can't remember the order on this, but somewhere down there are the YouTube videos. That's what I'll say, PHS111 YouTube videos. Click on that. That's a link that goes straight to the link. Now, when you get to that link, the videos you see at the top are those that I did last time I taught the course. The ones from this time are at the bottom, and at the bottom, the ones starting with syllabus, and then everyone after that, those are the ones we've done this term. I'll leave those others up there in case the system goes down, then you'll still have at least a YouTube video covering sort of the same material that'll be up there. Because I never know if the system's going to go down, they don't let us know ahead of time. So keep them all there, and then as I cover new material for this term, I take the one off for last term. So all the ones are there. Okay, and in the YouTube videos, you'll hear me go over the syllabus, go over the locator card, go over research paper, go over safety issues, go over everything, plus all the PowerPoints. Now, also on Blackboard will be the PowerPoints. Now, they're in a folder, and when you go to the right-hand side, and there's a symbol that's either up or down, I don't remember which, click on that, and the folder opens, and you can see all the ones. We've done the chapter 14, chapter 15, we're starting chapter 16 today. So the PowerPoints are there statically, but if you watch the YouTube videos, you'll hear me talk about it. I'll go through all the PowerPoints again on that. Okay. I think that's pretty, and there are some other files out there, like space objects in perspective. There's a folder with Hubble Space Telescope pictures in it, just things that students have sent me. They found interesting, so I put them out there so other students can look at them too. And that's pretty much it. So try to get caught up as soon as possible. And let's see, I think, is anyone else here who has not picked up the first lab? Okay. We'll be doing the second lab today. Now again, I think from one of the videos will say lab 1 on it, and then we didn't quite finish it, so the next day's video we'll finish that at the very beginning. So that's out there. And this is Shikaya. Okay, good deal. Anyone else come in while I wasn't watching? And I've called everybody's name, right? Okay. Now, so I did get all of the labs that were turned in graded, okay? However, I don't have them on Blackboard yet. So this is a new Blackboard. I haven't quite figured out how to get the grades on there yet, but hopefully tomorrow morning I'll have, maybe this evening and tomorrow morning I'll have some time to work on that. For those 4 people who took the first test, I have those graded, but I don't have them on Blackboard yet. I'll try to get that done this evening or tomorrow morning, if possible. Now, it seems like I saw an email from the dean that she's wanting me to add a bunch of second mini-term math classes, which we do every year, and then they cancel them and take them off, and then they want us to add them back the next term. So I'll be doing that for a while tomorrow morning. So, but if I can, I'll try to get the grades on Blackboard. Now, not everybody turned in the first lab. You got a week to work on it. That's fine. And of course, not everybody did the first test because you're waiting for your books. And I don't know why they don't have the books here, especially if they told you what, a week ago or more that they would be here at the beginning of last week, right?
Friday.
Okay. Okay. Right. This is crazy. All right. Any questions on anything we've done so far, or any other questions? Did that fill you in on most of what you need to know? Okay.
Did you get my email that I sent last week?
I doubt it. You see, I was out of town over the long weekend, and where I was, we had DSL, but the DSL wasn't working, so I couldn't get any emails from Thursday afternoon on.
My grandmother had died last week.
Oh, I'm so sorry.
So that's why I didn't
Got it. Okay. Well, do your best to get caught up, and if there's any way we can help, let us know. Yes?
What did you say that office hours for assistants?
For what?
The office hours?
What about office hours? Just for all my office hours?
For
Okay.
us to take the test.
Okay. Let's start with today. As soon as the class and lab are over with today, if you finish early and you want to take it then, you certainly can, because the second test is, yeah. Sure, yeah. Second test will be after the second lab today, okay? Now, tomorrow, 8 to 10, I'm in my office then, and then I have a small break from 11:40 until 12:30. Okay, so that's a time you can see me. My office is 265 down the hall there. Then I have a class that goes from, getting my times crossed up, 12:30 until 2:20. So from 2:20 until 3, no. Goodness. I'm having trouble remembering my office hours because they've been so weird. Let me see. I left my glasses at home, so it's hard for me to read this. Rakiria is here, right?
Yep.
And Donald is here. Okay. Now, let me go through these again. They're on Blackboard, and they're in the locator card. They're on my syllabus. They're everywhere like that. I'm trying to recreate my schedule tomorrow. 10 to 11:40 class. Then I have a 12:30 till 2:20 class. Is that right? No, 2:10. 2:10. Then, so from 2:10 until 2:30, I'm there. And then 3:45, I'm rushing to get to the Birmingham West Campus. So tomorrow, it's only 8 to 10, 11:40 until 12:30, and from 2:10 until 2:30. Okay? Now, Thursday, a lot like today, 8 to 8:30, that's it. And then 9:45 to 10, 11:15 to 11:30, and then 12:45 until 1:15. But then Thursday, after everything else is over, I'll be here till at least 6, so you can take it, that I can be here longer. Friday, 8 to 12 on the Birmingham West Campus. Okay. Now, if you wait till next week, Monday is better than any other day except Friday. Actually, better than Friday. 8 to 10, and then 3:45 till 6. So Monday, I have 2 blocks of office hours. Every other day is either little bitty pieces or only 1 block. Okay. All right. Any other questions? Good questions, by the way. Yes.
Is Monday this campus or the other campus?
What's this again?
This campus or the other campus?
What are you talking? What's that?
Mondays.
Mondays? Monday through Thursday I'm on this campus. Friday only I'm on the Birmingham West Campus. Okay. And by the way, I'm hard of hearing. That's why I have to have everything repeated a time or 2. All right. Any other questions? Good questions. Now, again, the Chapter 15 test is last 30 minutes a day, but if you don't feel ready because you don't have a book or just weren't ready, that's all right. You can take it later, but that's why I was going over office hours, to let you know when you can catch me. But if you are going to take it Friday, when I'm on the Birmingham West Campus, let me know Thursday so I can get your test or labs or whatever in my grade book to carry over to the Birmingham campus. All right. Any other questions? All right. Chapter 16. Okay, if you remember, chapter 14, we started with the universe, everything, okay? And then we narrowed down last chapter to the solar system, okay? Now we're narrowing down even further to the Earth in space, which includes a lot of the Earth-Moon system, okay? So we'll be talking a lot about the moon in this chapter as well. The title doesn't seem to indicate that, but that's a big part of what we'll talk about today. Here is the core concept, and this is located, if you have the big book, this is on page 407, or that corresponding page in the smaller text. The way the Earth moves in space is used to define time and describe the location on the surface and causes other recurrent phenomena such as the seasons. Now, we've already introduced a whole lot of the stuff that's just talked about here. Time we've talked about, location on the surface of the Earth we've talked about, and then a little bit about the seasons. Okay, so a lot of this is that kind of stuff. Now, here again is an artist drawing. Do not take this to mean to be absolutely factual. Number one, the sun is way too small in this picture, okay, compared to the other objects. Number two, I can't tell if they intend that little dot there to be Mercury. If it is, that's okay. It could be they intend that to be Venus, possible, okay. That, I'm pretty sure, is supposed to be the Earth, and what I think this is supposed to represent is our moon. So we're right next to the moon looking back at the Earth. I don't think the sizes, certainly they're not, if you're real close to the moon, it could look bigger than the Earth, just like we're on the Earth and our Earth looks bigger than the sun, but we know it's not, okay. Now, I can't tell what they mean this to be. I guess Jupiter, but I'm not sure on that. That obviously is supposed to be Saturn, and I think this is possibly Uranus and Neptune, supposedly out there. Mars doesn't show up anywhere here. I can't tell if Mercury is supposed to be there or not. But this is just sort of an artist's rendition. So don't get too carried away with that. The picture you have in your text on the opening page is a lot like this, just really blown up. It's actually a picture of the Earth taken from outer space. Okay. Yeah. By the way, the PowerPoints are all out there. If you want to print them off beforehand, you certainly can, then you can take notes on them. But if you don't want to do that, you don't have to. It's just a possibility. That's why they're all out there, so you can see them ahead of time if you want to. Yes.
Versions of this, can we use it to take the test?
Okay. Remember, you can have a single page, front and back. So to print off all the PowerPoints, unless you make them really small, it's going to be hard to get on a single page, front and back. But if you can do it, more power to you. Yeah, you can do that if you wish. Yeah. Or if there's just one or two of them that you think contain some really good stuff, you can use that front and back or something like that. All right. Where we begin then in 16.1 is the shape and size of the Earth. Now, if you've noticed the things we've been talking about, remember the orbits of the planets are not perfect circles. They're ellipses. Circular, but not really circles. Well, the shape of the Earth is close to being what they call an oblate spheroid, not a perfect sphere. Now, why do they call it oblate spheroid? Well, here's the deviations we've got. It's slightly pear-shaped. The bottom half of the Earth is a little bit bigger than the top half, okay? Slightly pear-shaped, slightly. Now, this makes no sense to me at all. They say there's a lump in the Pacific. Now, I have trouble understanding how an ocean can have a lump in it. Because you would think if it did, the water would run down off the lump, okay? So I'm not sure what they mean by that. Now, you can read your text and see what they say. And I don't recall, because this is a newer edition than the slide, if they have that same comment there. So that doesn't. Here's another one. Depression in the Indian Ocean. Well, it seems like to me if there was a depression in the Indian Ocean, the water would run into the depression and it would be flat.
When you
So,
say depression, you talking about a valley or something?
I do not know, and like I said, this is an older slide, but what they're saying is it isn't as perfectly spheroid as you would expect. Now, here I can understand. The elevations and depressions of deviations are less than 85 meters. Now this next slide sort of goes along with that. Well, first here's a picture of the Earth taken from outer space. I'm trying to see if there's anything we can really tell from that. I can't say for sure this, because mostly what you're seeing are clouds. And the clouds are obscuring the landmass, so I can't see where it is. But don't think that this is what the deviation is. This is because this is the phase of the Earth. This part is away from the sun. The sun's over here, and this part is being shadowed out. So the Earth does continue here. The picture just isn't a full Earth. It's a partial Earth. Okay? Well, don't worry. There's nothing but a picture there. Here's what they mean by the deviations. We're a little bit fatter around the middle, don't be making fun of me, here, and a little bit shorter top to bottom, okay? A perfect sphere would be that dotted circle in 3 dimensions there. We're a little more. Now, they've exaggerated this big time. Okay? But yet, on the other hand, these numbers aren't matching up too much. They said the elevations and depressions of deviations are less than 85 meters, they say here. But if you look at this, the difference between this and that is 42 kilometers, which is a lot more than 85 meters, okay? So that, I can't quite justify this, but the point is, it's a very small percent difference, okay? We're almost a perfect sphere, but not quite. A little fatter around the middle, a little shorter on the, okay, yes?
So, the perfect sphere is the dotted line.
The dotted line.
So why does it look more like an oval?
Well, this is actually the oval. I have the same optical illusion that you do. This makes that look like an oval, but that indeed is a perfect sphere. This is the oval. See, it's wider here and not quite as wide there. Okay. But superimposed on each other, it makes it look like the dotted one's the oval, because the other has more color and substance to it. Okay. So that's why we're not quite a perfect sphere. Yeah, everybody got it? Okay. Okay. Got it? Okay. Now, how is the Earth moving? Any of you feel like you're moving now? Well, we know you are. So here are some of them. 3 of these Earth's motions are completely independent of the motions of the sun and the galaxy. Doesn't matter what the sun and the galaxy are doing, these are completely independent. First of these is our yearly revolution about the sun. Now, Jerome, you look like you're sort of more in the middle of the class now. Will you be sun for the day? Okay? So if you're there, we are going around you. Okay? The Earth is going around the sun. It would make one complete circle all the way around once a year. That's our yearly revolution around the sun. Doesn't matter what the sun's doing, we're going around the sun. Now, not only that, but we're spinning. Maybe I should get my good old handy-dandy visual aid in. Yeah, it's all right. also spinning as we're going around. So we're spinning like this as we're going around good old sun there, the bright guy, okay? That's completely independent of what the sun and the galaxy are doing. Now this one, okay, going around the sun in a year, that doesn't seem like we're going too fast, but we are moving pretty fast on that. Daily rotation about the Earth's axis, it's moving pretty fast. This clockwise wobble of its rotation axis, that's incredibly slow, like that. No, I mean, all right, he's here. Good deal. Okay. Now, what does that mean? That means that right now, our axis is like this. In tens of thousands of years, it might move just a little bit. I'm going to speed this up a lot. This is what they mean by a wobble of the axis. So that takes tens of thousands of years to make one thing. So that is an incredibly slow wobble. Okay? What's that?
I got a dumb question.
Okay, no such thing. Okay?
Where are the axes?
The axis of the Earth is the line from South Pole to North Pole. That's what we spin around.
Okay, so
That's-
it's actually something there.
There's nothing there. I mean, okay. If I were a figure skater, which obviously I'm not, okay, and we do one of those
Squirrel.
twirls and stuff, the axis would be the straight line through me as long as I do. If there's no real thing there, it's just that would be what I'm spinning around. Okay. Same thing here. The North Pole doesn't spin, everything else moves around the North Pole. The North Pole sort of sits still and just does like this. Okay. That's the axis. All right. So those are the three motions of the Earth that are completely independent of other motions of the sun or the galaxy. Okay? Now, the next slide is going to show us all those other motions as well, including these three. Okay? So I'll wait till everybody is finished. Okay, everybody got it? No, there's still some writing? Okay. Now, again, in the text, on page 409, since some people are still writing, this is an artist's concept of the relative size of the 8 planets in the solar system, not to scale, okay? And you'll never see the planets like this. But this is the relative size. That's supposed to be Mercury. Of course, they don't touch like this or anything close to it. Venus and Earth. Earth is slightly bigger than Venus, but it doesn't look like it here. And then Mars. The 4, what are those interior planets called? The rocky planets. Another name for it is terrestrial planets. Then the asteroid belt that's not shown here. Compared to what these are, the little rocky planets, that's Jupiter back there. There's this great red spot. It is enormous compared to us. Okay? Then next to that is Saturn back there. It's huge. Not nearly as big as Jupiter, but still huge. And then there's Uranus and Neptune back there. Almost identical in size, just like Earth and Venus are very close in size. But these are still much, much bigger than those. The gas giants, much bigger. Now, the planets on the ecliptic, I wish they had this on the slide, but they don't. I know you can't see anything from where you are, but because the sun has the imaginary circle around it, that's the ecliptic, where the sun is relative to Earth, okay? All the other planets, because we're in that sort of plane, they're really close to the ecliptic. So this thing you'll see, I don't have my glasses on, so it's hard for me to read. Jupiter is off just a little bit. Saturn's off on the other side just a little bit. if I get far enough away, I can't read the writing. What's the one in your book that's pretty close to October? I'll have to stand up and get far away from it. The color contrast is pathetic too. There's Mars. Oh, I guess these are some stars they're naming too. There's Jupiter listed twice. Mercury. Seems like one of those should be Venus, but I can't see it. But anyway, they're awfully close to the sun on the ecliptic. Okay. Everybody got this one now? Okay. So here are all of the motions of the Earth through space. The 3 we just did plus this. There are 7 what they call conspicuous motions. Not that we can sense them, but we can sense things about them. First was our daily rotation. Here we are, spinning like crazy. Okay? At the equator, we're spinning at 1,670 kilometers per hour. That's how fast the equator is going. Okay, in miles per hour, that would be close to 1,000. It would be 900, between 960 and 1,000 miles per hour at the equator. Now, at the north and south poles, hardly moving at all because they're spinning, but they're not moving. But at the surface, they're moving. At the equator, they're moving very, very fast because we're a fairly good-sized planet. Okay, the monthly rotation about the Earth-Moon center of mass. Now, that may not make any sense to you now. A little bit later in the chapter, we'll talk about that, and it'll make some sense. But remember, hopefully you do remember this, for our size Earth, which is not that big, our moon is the biggest moon for this size planet. There are some bigger moons out there, but they're around huge planets, okay? So our moon to Earth ratio is the biggest moon to Earth ratio of any of the planets, yeah.
So it's like actually.
So what?
So if the moon was like the Earth, it's habitable and water, oxygen, nitrogen, just with Earth, and could it be classified as a satellite planet orbiting around the Earth? I mean, would the moon also be a planet?
No, it wouldn't be a planet. If it's going around the Earth, it's a satellite of the Earth. If it's going around the Sun, it's a satellite of the Sun. Now, well, I almost thought you were asking if we were a binary planet. That might be, but you're getting close to what I was getting at here. The moon's out here. Now, the moon, if this is the Earth size, the moon would be something like this, I'm guessing. So that's not nearly as big as the Earth, but relative to other moon-Earth systems, that's huge. Okay, but because it's got enough mass in it, when it goes around the Earth also is not quite a wobble, but it moves, its orbit moves, because gravity, any two objects pull on each other. And when they're close to the same mass, they pull more on each other. Now, Earth's mass is a great deal more than the moon, but even the big moons around Jupiter is so massive, Jupiter doesn't even notice that. But we do a little bit of a monthly rotation about the Earth-Moon center of mass. Okay? Now, the yearly rotation about the Sun, from the time it takes us to be here, go all the way around the Sun, and come back to here again, that's going at about 106,000 kilometers per hour, which would be about 70,000 miles an hour. Okay? That's our rotation around the Sun. Now, our solar system orbits galactic nucleus. There are bunches of stars right in there, and then it has those spiral bands that go out from that. We're about 2/3 of the way out one of those spiral bands, and we're flying around the center of the Milky Way. That's going at about 370,000 kilometers per hour, which would be 250,000 miles per hour. Flying around there. Well, of course, we don't notice because we're on the Earth. We don't sense that. Number 5, our orbital motion within the sun's local star group. Okay? Now, we have a little star group of other stars. They don't mention how many there are, but we're going an orbital motion within that of about 1 million kilometers per hour, which is about 600,000 miles per hour. Man! Okay? And then the motion of the Milky Way galaxy relative to remote galaxies, like Andromeda or some of those others, that is about 580,000 kilometers per hour, which would be about 350,000 miles per hour, approximately. And then we have some minor motions, okay? The changes in shape of and size of the Earth's orbit. Okay? Now, we'll talk about this a little bit later, too. We may have mentioned it before, but here we'll get into it. Say again? Oh, okay, yeah. I'm going to describe this first. Okay. Right now in January, do you think we're closer to the sun or further than the sun than we are other times of year? No, actually, we're closer. Yes, but the thing is, it's the tilt of the Earth that makes us be winter time now, because there's the sun over there, and right now we're tilted away from the sun. Okay, so that makes us cold here. But we're actually a little bit, not much, but a little bit closer to the sun than we will be in July.
So we're closer to the sun, but we're tilted away from it.
But we're tilted away from it. That's it, exactly. So in July, we'll be just a little further, not a lot further, just a little further away, but tilted toward the sun, so therefore we're hotter. Think about the poor southern hemisphere. Right now, they're closer to the sun and tilted toward it, and in July, they'll be tilted away from it and further away from it. So their extremes between temperatures winter and summer should be a little bit greater than ours. And what seems to be happening in Australia right now? Fires, okay? Incredibly, because they've had some incredibly hot seasons down there, okay? So I don't know if that's part of it, but it seems like it would have to be. So what I'm getting at there, when we're closer to the sun, our orbit is not a circular orbit. We're elliptical. When we're closer, we're moving a little faster. When we're further away, we're moving a little slower. So that's what it means, changes in shape and size of the Earth's orbit. So those are some minor changes there. Changes in the tilt of the Earth's axis, we talked about that. That's a very, very slow change. We'll never see any evidence of that in our lifetime. Now here's the other thing. The old Earth is getting old and tired. It's spinning a little more slowly than it did a long time ago. But again, that's an incredibly slow change. We don't notice it. It's still very close to 24 hours to rotate once. So I didn't do that. Okay, there it comes back. I think. There it comes. Okay. Everybody got it? Still working on it? Okay. Those are 7 conspicuous motions of the Earth. Actually, it's 9 because minor motions is 3 of those. So that would be 8 and 9. But the big ones are pretty major. But do we even notice them? No, because we're fixed on the surface of the Earth. Now, if I can, since y'all are having such trouble with the bookstore, I'm going to try to get down there in the morning if I can squeeze it in all the other things I'm trying to do in the morning and see what I can figure out too, because this is kind of ridiculous.
Come next week, it'll be too late to even get a book from him.
Yeah, well, and you have a pile of reading to do if you're waiting to read everything before, but I'll see if I can figure out what's going on. So maybe I'll let you know something on Thursday. They may be in by tomorrow, I don't know, but I also want to make sure he's got them down for the second mini-term so we don't live through this again, because that's an even bigger class.
They had the second mini-term folks in there.
They do?
Have the first mini-term.
That makes no sense at
Yeah,
all.
they were completely out of the first mini-term, but had some of the second mini-term.
Okay. All right. Not yet? All right. So we're flying along here, but of course we don't notice anything because we're on the inertial system of the Earth. We just think we're here. We
It's
think,
amazing that we're just here and everything's happening out in the universe.
right. Yeah, it is really amazing. And the speed at which things are happening are pretty amazing too. This bright sunlight coming in makes it sort of hard for me to read because I see a lot of glare. But can y'all read this okay? Would it help to turn off the other lights there? Don't think so. We can try if you want to, because there's plenty of light coming in. If you want to hit the switch, David, does that make it any easier? I don't want Jerome falling asleep on us now. Okay. I'm just kidding. You rather have it on or off? Off? Okay. Okay. Okay? Anyone else need it longer? Okay. So let's discuss in a little bit more about what the Earth's motion in space is like. Overall, if you were out there in space somewhere looking at the Earth moving, we appear to be moving along a helix at an incredibly fast rate of speed. Because remember, we're spinning. We're also going around the sun really fast, but the sun's going around the center of the Milky Way really fast, so we're doing this kind of stuff because we're having to keep up with the sun. And so you add all those three things together, we are flying at fantastic speeds through space. Now, viewed from the Earth, we're sitting still. We're not, but it seems that way. And on the ecliptic plane, that's the plane of the Earth's orbit around the sun, it looks like the sun is going around the Earth. Okay? It's not. We're spinning and makes it look that way. The planets are also, the other 7 planets are also moving in a very narrow band near that ecliptic plane. Okay? Because the solar system, or at least the 8-planet solar system, with the sun included, is relatively flat. Remember, the Oort cloud of comets is huge. It's near spherical. The Kuiper belt is a much fatter band than what our solar system is, the 8 planets. Now, the sun moves along the ecliptic. See, up here they say the plane of the Earth's orbit around the sun, but then they say the sun moves along the ecliptic because that's what it apparently does. And as it's moving, the background stars are always changing. Now, get this, the stars are fixed out there, and the sun's pretty much fixed. We're moving. We're moving this way, making the sun appear to move on a daily basis. It's not, it's fixed. But we're also moving like this. Now, the stars are fixed. So right now, I'm looking at the sun. I can't see any of the stars on that part. I can see all the stars back here because they're away from the sun. I see them at nighttime. Okay? So I see all these stars, none of those because that's the daytime. Now they're in the daytime. I move over here about 3 months later, and I can't see these because the sun's blotting them out, but I see all these over here. Okay, these I see just a little bit, morning or evening or something like this. These I see big time. Okay, move on over here, somewhere back here, and now the ones I couldn't see before when I was over there, I can see really well. Those over there I was seeing really well, I don't see now. So you see, it looks like the stars are moving on an annual basis around the ecliptic. And when I get over here, I can see all these stars like crazy. And those over there that I couldn't see when I was there, no, that's not right. Yeah, I can't see now because I can see them well, can't see them now because the sun's blotting them out. So it makes it seem like the background stars are moving. They're not. They're fixed in space. But because of my motion around the sun, it makes them look like they're moving on that same ecliptic. So that's what they're meaning here. The sun moves along the ecliptic across the background stars. Okay. That's the apparent. Okay. It looks like there is another slide here. Let me bring it up. Oh, this is the helix. Okay, we're moving around the sun, but the sun's moving around the center of the Milky Way, so we're really doing this kind of number. Okay, kind of like a corkscrew. And then our little moon is going around us like this. It is one like that, you know, so that tends to be how we're proceeding that way. Incredible the speeds that all this is happening. Okay. Still working on this slide. Now, do our stars out there change much? Okay. This is such a big universe. For us to go from here to here, you would think it'd make a big difference. That's tiny compared to the size of the universe. So we don't notice a lot of difference in those stars year to year to year. There is a little bit, and we'll talk about that a little bit more later too. Okay, everybody finish this slide? Okay. Revolution. No, this is moving around the sun. Our revolution is basically, the rotation is our spinning on our axis, revolution is our movement around the sun. That orbit defines the plane of the ecliptic. Where we are relative to the sun is fixed pretty much, we're going around it, that plane is our ecliptic, okay? That orbit. Of course, what it seems to us is the background stars seem to be moving along that. The ecliptic is the apparent path of the sun through the heavens as seen from Earth. Whereas in reality, it's us moving around the sun, but it makes it look like the sun is changing in itself. Now, our orbit around the sun, these two words are similar, but they're different. Ecliptic is when the sun is eclipsing the stars behind it. You can't see them because the sun's too bright. The elliptic orbit, that means we don't follow a circular orbit, it's elliptical, slightly elliptical. Now, we're talking about the relative sizes. 2.5 million kilometers closer in January than we will be in July. 2.5 million kilometers more distance in July. Now that's the sun. Now, is that a lot? Well, 2.5 million kilometers would be about 900,000 miles, I think. 900,000 miles closer in January, 900,000 miles more distance. That's out of 93 million miles. So that's a very small percent. It's not going to make a lot of difference to anything, okay? But we actually do receive about 6% more solar energy in January than we do in July. But most of that is picked up in the southern hemisphere, not where we live. So that's why the southern hemisphere should have greater ranges in temperatures summer to winter. I haven't seen any data on that, but it seems like that would be the case. So actually now we are closer to the sun than we will be just about any other time of the year. I think it was around January 4th was the closest date. And we're just a little bit further than that now. But we're tilted away, so we're feeling much colder. That is not what causes temperature change. It's the tilt, as we said earlier.
The tip does not cause it?
No, this fact here, that we're a little bit closer to the sun now than we will be in July. That doesn't, it affects a little bit. I mean, 6%. But that's scattered over the entire Earth, so it's not a major thing for us at all. The tilt, though, that's the major thing. I think we'll get to that either in the next slide or two. Let me keep turning my page. All right, the motions of the Earth, by the way, we're in 16.2. All right. Now, what we're talking about in the slide set, it calls it revolution. In this book here, we're calling it orbit. Okay, same idea, but just different names for it.
Dr. Fowler?
Yes.
On the test, we should be more interested in the ecliptical orbit not being circular or how far it is in January.
All right. Okay. The numbers generally aren't so important. I think you'll see that some big ones, like in the first chapter, we talked about the relative age of the stars. You know, big stars, little stars. You know, need to have the general idea of how old the star will be before it dies, but not the specific. The specific numbers here, this is just to give you a concept. The idea is we're closer in January than we are in July. It seems counterintuitive, but we are. So the actual number's not as important. Okay. Anyone still need it a little longer? I'll see one. The revolution is important, minorly because of the changes in distance, but we're definitely elliptical. That's why there's a change there. But the major thing is the tilt, and that combines with the other to create the differences we are used to seeing and the reasons for those. Okay? Okay? All right. Now, this is exaggerated, big time, okay? But they're doing it for effect, okay? In what we consider well, let's start where we are now. Okay, here is last December. Okay, we were closer to the sun, got even closer in early January, but we were tilted. The southern hemisphere was tilted at that what angle? 23.5 degrees. Always. We're always tilted at that. Okay? But that's when the South Pole is pointed most directly at the sun, is in December. Varies from 21st, 22nd, 23rd, somewhere in there. North Pole tilted as far away as possible. Now, one thing they haven't shown on here, but if they did, they would show a little circle up here around the North Pole. What would we name that circle? The Arctic Circle. And down here around the South Pole, the Antarctic Circle. Inside that circle, around the 21st, 22nd, 23rd of December, the sun never sets in Antarctica. Anywhere inside that circle. Same playing up here, the sun never rises. Okay? Now, does that mean it's really warm down here in Antarctica? No. Still really cold. The reason is, if you look at this, the direct radiation from the sun always is coming in close to the equator. In fact, direct radiation is always between, guess how many degrees? 23.5 degrees south of to up to 23.5 degrees north of the equator. Always directly overhead, somewhere in that band every day of the year. Okay? Never directly overhead outside that band. Okay? Close, but never directly overhead. Syene, Egypt. Remember that was in 25 degrees north, right there. Now what is this circle down here? It's 23.5 degrees below the equator. What's that circle called? Tropic of Capricorn. And the one up here in the north? Tropic of Cancer, exactly. Inside there, that's the tropics. Between those two tropic circles, then that band in there is always warm, and it's almost like there's summer all year long. Okay? Just like, say again? What's that? Because of more direct radiation from the sun is hitting the planet there. And the fat part in the middle is closer to the sun, right? Yeah. So, and that's always is. The sun is coming in directly somewhere in that band all the time. All the time. Out here it's coming in obliquely. When it's obliquely, it has to go through more atmosphere and it loses more heat. Because the atmosphere is the same distance from the surface all the time. Okay? You're the sun again, right? Okay. The sun has to go through this much atmosphere here. It goes through this much here because there's more atmosphere because it comes in at an angle. So it goes through more and loses more energy. Up here, even when that's pointed toward you, it's so much angle. It's very, very cold.
But the middle part get a direct hit all the time.
Direct hit somewhere in that middle part all the time. You're right. Yes.
It may be a dumb question.
No such thing, if you ask.
So, I don't know if anyone of you guys or girls done this.
It's
You
what?
stare into the sun, and you start seeing your eyes start changing colors and start seeing the circular portion of the sun. Would that be the accurate size of the sun?
Okay.
You know when you stare at it too long,
Okay.
and you start seeing the outline of it through the glare?
Okay. If you're looking at the sun,
Yes.
okay, what you're doing is damaging your retina. Okay. Because,
do it,
yeah, yeah,
but not really all the time.
yeah, but don't do it. Yeah,
I'm just
no.
asking when your eyes start shifting colors and start showing that where the circular part of the sun is that the shape, the outline of the sun, or that's just your eyes just missing.
Okay. I can't say for sure because some of that could be your eyes' reaction to all that direct sunlight, and some of it could be actually what you may be seeing. But I think it's mostly your eyes' reaction. And they're saying, "Get me out of here," you know, I don't want to do this anymore because they shouldn't be doing it anymore. They say even during the solar eclipse that we had a few years ago, don't look directly at the sun, look at a reflection, okay? Because you can really have some problems. Now,
Those glasses.
what's that? Yeah. And if you use welder's glasses, those are the best thing
They
for
say
it.
more
Yeah,
solar.
and they have other glasses.
During the solar eclipse.
What's that?
They said more solar radiation comes during the solar eclipse. I don't know how true it is.
Yeah.
'Cause I remember the one 2 years ago. I was
Yeah.
in lab.
Yeah.
In high school.
It's you always be careful, okay, about looking toward the sun. So here's where, even though we're closer to the sun, that doesn't matter. And this is a gross exaggeration. The difference is minuscule, okay. Now, over here on March 21st and September 22nd and 23rd, what's happening then?
What you said, what month?
March 21st or 2nd, 20th or 21st, and September 22nd, 23rd, what's happening then?
What I ain't heard.
The sun is directly over the equator. And those are called what times of the year? No, that's here. December and June, that's the,
The equinox?
yeah, that's the equinox. So equal day, equal night, every place on the planet, 12-12. We did that the last lab, right? Okay. This one is what we call winter solstice for us. Summer solstice if you're in Australia. This would be summer solstice when we're tilted most toward the sun, and that would be winter solstice for southern hemisphere.
So, at the southern hemisphere, so us, the sun is sitting below the horizon more to the horizon.
Right. Right now, the sun rises south of east and sets south of west
That's what I
because it's further down. Okay?
you know,
Whereas in Australia, it's right now at this time of year, it's rising north of east and setting north of west. And that's the big arc across the sky, and that's their summer down there.
so in winter, because the sun is set north of east, north of west, it's set south of east and south of west.
Okay, I missed the last part.
For their, for Australia in summer,
Yeah.
the sun doesn't set north of east and north of west, it sets north of east and south of east and south of west, like it is here now.
Yeah. Okay. Yeah. That's yeah. For them, yeah. That's what they see. Yeah. Because it goes rises south of east and then goes way up there and then comes back down. So it's up in the sky longer because of that. Yeah. Because they're down here. You're absolutely right. Okay. So this is winter solstice for the northern hemisphere. Swing equinox, autumnal equinox. This is summer solstice here. What did I say solstice stood for? Sol is sun, solar system, sun, S-O-L. Steel, stees. It quits rising or quits falling. Quits rising in the summer, quits falling in the winter. Because every day, right now, if you look at the sun at our dead noon every day, you'd see tomorrow would be just a little higher than it was dead noon today. Then the next day a little higher. Keeps going up until June the 21st or sometime in there, 21st, 22nd. It reaches the highest it's going to be, wherever you happen to be, the highest it's going to be on the northern hemisphere. And then it doesn't rise any higher, and then it starts falling again. Okay? So that's that. Now, obviously, the sun's way too small in this picture. The dimensions are completely out of whack. These are exaggerated extremes here, but they did that for a purpose. Okay. And notice here, no matter what time of day, the Earth's spinning on this axis. Up here, sun never rises. Down here, sun never sets. Here, the sun never rises. Here, the sun never sets. It gets low in the sky, but it never sets. When it never rises, it never gets very high in the sky either, okay? It just stays along horizon a little bit higher at noon, a little bit lower at midnight. But it doesn't get very high. That's why there's not that much direct radiation going toward it. All right, can we move on? Okay. Now, let's talk about the spinning of the Earth. That's the rotation. That's basically on page 412. Now, there's a couple of examples here before we get there. What is the latitude of an observer who measures the sun's altitude of 38 degrees above the southern horizon at noon on the summer solstice? Goodness gracious, what a mess. Okay? It's the kind of thing we did in the thing when we drew our pictures. You just have to back through it. That would be about, says 75 degrees north. Yeah, that sounds reasonable. And 16.2, what is the latitude of an observer who measures the sun's altitude at 40 degrees above the northern horizon as the sun at noon, northern horizon at noon on the summer solstice? You'd have to be in the southern hemisphere, and they say about 26.5 degrees south. There's a little concept supplied on sunrise, sunset. You can read that if you'd like. Now let's talk about rotation and the Earth's axis. As we've said several times, the Earth's rotational axis is inclined at an angle of about 23.5 degrees as shown. So let's see if it'll show it. Yeah, there it is. This angle between our actual equator here and the ecliptic there is 23.5 degrees, the maximum. This would be winter solstice here, where the sun is below the celestial equator. Okay? Autumnal equinox and spring equinox, those two great circles coincide. Summer solstice, the sun is above the celestial equator by 23.5 degrees. Okay. Now, so the Earth's rotation axis inclined at that 23.5 degrees. What are our seasons then? They're determined by the orientation of that rotation axis. The winter solstice, over here, when the sun is as far to the south of the celestial equator as it can get, okay, then that's the beginning of what we call winter. Winter solstice. Around December 21st or so. Okay? As low as the sun will ever get. That begins our winter. That goes until spring equinox. Spring equinox, the sun has come up a little bit every day, until it sits right on the celestial equator. That's spring equinox. That's the end of winter, beginning of spring. Then spring, the sun rises above, keeps going up and up and up until summer solstice. That defines our spring, between spring equinox and summer solstice. March 21st till June 21st approximately. It varies year by year. Okay? Then, at that summer solstice, that begins our summer season. It goes till autumnal equinox when they cross again, and then that's our summer. And then autumn or fall is between autumnal equinox and winter solstice. Now, the celestial equator, it seems like this was already defined a long time ago. If this is the Earth here, tilted at 23.5 degrees, then the celestial equator is that pink circle there. That would be projection of that outward onto the celestial sphere. Of course, the North Star is always directly over the North Pole, the northern axis of the spin of the Earth. Fortunately for those in the southern hemisphere, there is no South Pole star. You look out there due south, you hardly see any stars at all. I mean, it's just a big blank part of space there. Okay. We have a North Star. Okay. Yes?
There's something in the South Pole that no folk in the southern hemisphere, the northern hemisphere don't see.
Say that one more time.
There's two objects in the southern hemisphere.
Two constellations? No.
Objects.
Objects.
Or celestial bodies.
Got
In the southern hemisphere and the northern hemisphere, that's see.
it.
The small and the large Magellanic Clouds.
Small and large what?
Magellanic Clouds.
Okay.
The satellite galaxies that open out.
Okay.
We don't see it here in the northern hemisphere.
Right. There's a lot of things. I mean, for instance, there's a constellation or something they call down there the Southern Cross. It's a very distinct 4 stars that make almost a perfect cross. You can't see it in the northern hemisphere because it's down there, okay? And they see it maybe not all year long, but most of the time. And that's one of their big constellations. So yeah, things like this. And when you said Magellan, somewhere in that, Magellan, why him? Magellan was the first to circumnavigate the globe. Means he was the first one to go around the very tip of South America, which is miserable waters down there. You got the Atlantic Ocean on this side, Pacific Ocean on this side. They do not mix and marry very well. The currents, the winds, the temperatures. This is really cold down there. And actually, I heard there was a team, the first team that has rowed from South America to Antarctica. Now, that's the closest, but that's still a long way. And that's some of the nastiest, worst, stormiest regions on the planet. And this team, I can't remember how many there were, maybe 6 or 8 guys that went and did it by hand, rowed from here to there. And they said, I think they're not going to do it again. You know,
So how did they get back? They rolled back through the passage.
I think once they got to Antarctica, they caught a plane and came home. You know, I don't think they rolled back, right? But they said the day that the last day of rowing, amazingly, everything got perfectly calm. It was like going on.
It's probably praying the whole time.
I think so. Yeah, I would have been if I wasn't throwing up. Yes, but that just has happened. If anyone can find anything on that, that might be a really good paper topic. Okay. So yeah, and Magellan was the first one to go around there. So those sites he saw, that's why it got its name. And I didn't know there was a cloud. Is it sort of like part of the Milky Way or something?
No, it's there. They don't individual. It's 2 galaxies that orbit very close to each other around the Milky Way.
Oh, okay.
They're satellite galaxies.
Yeah, like smaller galaxies. Yeah.
Andromeda has to be
Yeah, right.
2 different.
Yeah, I think mentioned one of those earlier, or maybe I forgot to mention it, but actually one of those we're disrupting. And this is the incredible thing. Even though the galaxies seem like the stars are so dense, these 2 galaxies could do like this and not be affected by either one. There is more space between us than there's space in us. And we could actually do like this and no collisions ever happen.
And why nobody talks about the triangular galaxy?
I haven't heard anything about those.
That's the other major galaxy.
I've heard irregular, and maybe that's part of triangular.
No, that galaxy's name is triangular.
Oh, I see.
There's a part about what the group is a smaller galaxy, but it's a part of the 3 major galaxies.
Oh, I see. That's why it's called triangular, because there's 3 of them. Yeah, okay. Is Andromeda, Milky Way, 2 of those 3? And then the other one's the 3rd. Okay. All right. Now, wait a minute. You're telling me the Earth is spinning. How do I know the Earth is spinning? I sure don't feel like I'm spinning. Some days I feel like I'm spinning my wheels, but that's beside the point. All right. Here are some ways. Yeah, okay. Here's some ways. And this is what convinced Galileo to start believing Copernicus. Because when he got his telescope set up, he was able to see Jupiter and see it was a huge planet, and he could see it spinning. Because Jupiter, if you turn back to that last chapter, Jupiter is spinning on its axis incredibly fast, and as big as that is, boy, on its equator is flying. He could actually see it spinning. Not per se, but night after night, he could see that great red spot had moved. So he knew it was spinning. They've done the same thing with the sun, and I think you'll see on figure 16.8, don't look at the sun for this, but look at pictures of the sun, and you can see that these sunspots are moving. Well, if the sun is spinning, Jupiter is spinning, hey, why wouldn't Earth be spinning? So that's one. Now here's the other. I'm not even sure how I'm pronouncing this. Foucault pendulum, I think is how you say it. Yeah. He was a Frenchman, I think. That's somebody you could write on if you wanted to, or what's this experiment with his pendulum? And I don't know if they still have one at McLean Science Center. Have y'all been in there lately? Okay. They used to have this big old pendulum that swung. I mean, it was an area, much bigger than this room that it swept. Okay? Big old thing, way up high in the ceiling, and it swept. Now, you wouldn't notice after a swing or two it was moving. I mean, you know it's moving this way. But if you came back 4 hours later or 6 hours later, you'd find it was swinging that way. And then it was swinging this way. It's slowly changing. That's because the Earth is spinning. Foucault pendulum, the pendulum oscillates in a fixed direction. The orientation changes as the Earth rotates. Okay? So there's the second. Other celestial bodies are seen to be rotating. Foucault pendulum doesn't follow just one line back and forth and back and forth. It actually, over a 24-hour period, makes one complete circle around the arc around the circle, or something like that. And then the third one is the Coriolis effect. Now, there's another name if you want to write on who he was. That's deflection of paths as the Earth rotates beneath moving objects. Now, the bombardiers in World War II and subsequent wars, when those jets that flew very, very high, when they dropped the bombs, they had to account for the Earth's spin. Because if they dropped the bomb from here, if the Earth was spinning, it would land here rather than where they aimed for. So they had to take that into account. And that's when some of the earliest time we learned the Coriolis effect. It's deflection of paths as the Earth rotates beneath moving objects. Now remember that huge storm, the Great Red Spot on Jupiter that we talked about in the last chapter? Remember I just said Jupiter is spinning really fast, so therefore it has a great deal stronger Coriolis force. Our storms today, tornadoes, hurricanes, and things like this, they spin because of the same fact, Coriolis effect. What you have there is low pressure mostly, and with the low pressure, the air is rushing. Yeah, it's sucking down, and as it's going down, because of the Earth's spin, it also creates this twisting motion. And that's why tornadoes and hurricanes have a distinct, usually counterclockwise rotation. Now, another dumb physics story. And this, I witnessed a first-hand telling of it. Okay. When I was at Georgia Tech as an undergraduate, I believe I was an undergraduate. I had this guy for both the graduate course and undergraduate. I believe it was in my undergraduate. I can't think of his name now. Dr. I can't remember it. You wouldn't know it anyway. But anyway, he was a crystallographer. That was his area of physics and he was the chief editor of the International Crystallographic Journal. He was a honcho, okay? So as chief editor of the journal, the International Crystallography Society at some point had decided to have its meetings in Rio de Janeiro, okay? That's down in Brazil. South of the equator, not too far below the Tropic of Capricorn. In fact, it seems like it's right on. And from what I understand, it was the party city of the Southern Hemisphere. I mean, they knew how to party in Rio. You hear people talk about Rio. They just call it Rio. Rio de Janeiro. That means river of something. January, I don't know what it means. But anyway, it's a big party city. Okay? So his international meetings, it's his first time crossing the equator. And he said when he got there, he couldn't wait. When he finally arrived, got up to his hotel room, he could not wait to go into the bathroom and flush the toilet. Because that's a low pressure system and the water goes clockwise there, not counterclockwise. Okay, that shows how sick a physicist is. I mean, if he's in the party city of the Southern Hemisphere and what he wants to do is run up and flush the toilet. Okay. Say again?
Which direction the toilet flush?
Okay, in the Northern Hemisphere, because it's low pressure, it always goes counterclockwise. In the Southern Hemisphere, it goes clockwise.
You sure that it doesn't,
I've never seen that before.
you sure it doesn't, matter if the, you sure the water that's coming from the toilet bowl is
Okay.
flushing this way?
Okay, if you're forcing it one way or another, that's one thing. But I say, okay, don't do that. Just pull the plug on the sink. Run a sink full of water, pull the plug. You'll see it goes counterclockwise. You haven't done anything to force that. That happens because of the Earth spin. On the equator, it just goes down.
Okay.
In the Northern Hemisphere, it runs counterclockwise. In Southern Hemisphere, it spins clockwise. Coriolis effect. That shows you the Earth is spinning.
I won't forget that word there.
What's that?
I won't forget that word there.
Okay. And go home and try it. Run that sink full of water, pull the plug, and you'll see it always is a circular motion. Unless you happen to be on the equator. Okay. Southern Hemisphere, clockwise. Okay. Now, the writing's still there. Here's another thing you could do. If you have a rotating stool, like they have, now this is different, not the toilet, okay. Rotating stool, like they have in a lab, and you're doing that, and you have a beam here and a thing over it, that thing's going like this, but as you turn the stool, it's still doing back and forth like this, but that's changing. That's exactly what a Foucault pendulum is doing. Very same thing, and that's why the Foucault pendulum is over a long period of time is cutting different arcs all the time. All the time.
So the stool is the Earth and the little thing doing that.
Yeah.
It's the
Okay, I can't
I
hear.
had that in my head. I can't remember.
Oh.
what it's
Okay.
too young for this.
What's that? Okay. Everybody finished with this one? Now, remember that little wobble in the Earth's axis? That's called precession. Okay? A very slow wobble of the Earth's rotational axis. Now, this is a reaction of the Earth to the gravitational pull of the equatorial bulge of both our moon, which is so close, and the sun, which is so huge. The combination of those makes us wobble a little bit. Okay? How much? How fast? 26,000 years for one precession to occur. And we're not going to notice it in our lifetime at all. Period. Okay? It changes the direction of rotation on the celestial sphere ever so slightly. Polaris was not always our North Star. If you remember when we did the star chart in the first lab, and also this causes slight changes in the equinoxes on the zodiac because we're wobbling just ever so slightly. The original zodiacs were right on the equator, ecliptic, when they first named them. And all those constellations were right there. That's been so long ago that there now some of them are slightly off of that ecliptic. And others look like they'd be better, but they don't change them. Okay? So people who follow horoscopes, it's changing, folks.
Do you believe in horoscopes?
No. Okay. I have read them before just to see whatever they mean.
It's
Yeah.
for entertainment.
Huh?
It's for entertainment.
Yeah, exactly. Now, here's what we mean. Any of you ever remember throwing a top? Oh, you do, okay?
What kind of time?
A top,
Oh,
that kind of top.
I've been there.
Okay. Back in the old days, that was entertainment for kids, Now we have cell phones, so they don't do things anymore, okay? But anyway, you spun a top, and if you did it real fast, that thing would stand straight up and just spin like crazy. But as it slowed, you'd see a little wobble happen. That's precession.
I
Yeah.
spun a quarter diamond in pink.
Yeah.
I spun a
Yeah.
quarter
And after a while,
stop.
right before it falls, it'll start to wobble. Same type principle. That's what precession is. The Earth is doing this. Not this markedly, okay? It's just a little bit, okay? So therefore, the constellations that would be here, they're not going to be here when it's over there, okay? They would be checked. But this is way exaggerated. But here is what we mean by that. The Earth, in its slight wobble, the North Star today was here in AD 14,000. Any of you going to be around? Okay. Not me.
I hope not.
Okay. Vega will be our North Star. So there will be some time or another between then and now that you probably will pass through a portion of the sky that there's no direct North Star. We'll use the North Star as long as we can, then we'll maybe find another one sort of close. Some of them will be very vague. Vega is a very bright star, though. So 14, yeah.
Even during this precession, the southern hemisphere will not have a southern star.
Possibly, but you see, the southern hemisphere just doesn't seem to have as many stars as we do up here. So it could be at some time in that one star will be really close to the South Pole. So I'm not familiar enough with the southern hemisphere to know, but it seems like something will be pretty close, you would think. But it's just such a big black hole, not a literal black hole, but a starless hole down there that there may not be anything. Okay? But that's what it is. North Star, what we call Polaris, our North Star, will not always be our North Star. In our lifetime, it will. Okay? Nowhere, nothing, we'll never notice a change in our lifetime. In 14,000 years, we'll notice a change, but not me. Okay? That's precession. Very, very, very slow motion. All the others are flying. This one is so slow you will never notice it. So that's about 12,000 years from now. Because it takes 26,000 years for one change. Okay. Everybody got it? Okay. Now, this next blurb here, 16.3, place and time. All right. Now, about 2 or 3 labs from now, we'll actually be doing this in lab. There are only so many labs you can do that relate to what we're doing here, and some of the chapters, like plate tectonics, you can't move plates around, so we're going to do something else in that chapter. Maybe it's the one that we'll do, place, especially the place part. The Earth's periodic motions provide a basis for determining place and time. Now they're going to do these slightly differently, separately. Rotation provides an axis. Because we're rotating, that means we're rotating about something that provides an axis. Well, that axis is our good old North Pole, okay, and South Pole. That's the axis there, okay? That's 1 point, 2 points on the globe that we can identify. Well, let's do this. Let's take equal distance between those 2 points. And what would we call that place? Equal distance between the 2 points. Not quite, but close. Equator. Equal distance between the North and South Pole. That's that ring around the ring around the moon. Okay? All right, you remember that, okay? Now, so that rotation provides us a North and a South Pole and an equator, okay? Between those 2 things, we can determine certain aspects of rotation. Now, the combination of rotation and revolution determines the cycles that can be used for time standards, as in equinoxes, equal day, equal time, night, okay? Solstices, max daylight, minimum darkness, and vice versa, okay? So that gives us basically our seasons. So the combination of rotation and revolution can do that for us. So this is a little bit of location, our axis and our equator. This is a little bit of the time, place and time. Okay? Now, given that equator and that North Pole, you know they've got to be what angle between them? 90 degrees. So make the equator 0 degrees, and then split that. There's 45, there's 30, there's 60. Split it into degrees, and you have 0 to 90. That's where we are. We happen to be 33 degrees, 23 minutes, 45 seconds north of the equator. It's a little over 1/3 of between the equator and the North Pole. Okay, so we're very much in the temperate region. A little more toward the subtropical region than we are temperate, but we're in the temperate region. Okay. Now, time. 1 spin of the axis is basically a day. 1 revolution around the sun is basically a year. But because we have these locations, like fall equinox or autumnal equinox, winter solstice, spring equinox, summer solstice, we can divide that year into 4 equal seasons. Okay? Now, is there any reason we have 12 months? 4 seasons, I can understand that.
Go ahead, you said.
Second?
You were saying, is there any reason?
Reason we have 12 months.
Because the seasons change. We're rotating.
Okay, we're rotating, that's for sure. But what? Okay, now think of the word month. What word almost is in month? M-O-N. What if you put another letter in there? double that vowel. Moon. The moon is what determines our months, approximately. Not exact, but approximately. So therefore, we have rotation and revolution. That determines year and day and seasons. Okay, all those are covered by that. But the months, that's determined by the moons. Now, why in the world do we have 7 days in a week? As far as I know, the only reason is biblical. Okay, that's the only reason I can think of that. Okay, but then on the other hand, you divide a month into 4 pieces. For instance, the first quarter of the moon, the second quarter, third quarter, and fourth quarter. That would be a reason. That would be about 7 days. So that may be the other reason for that. Everybody got this done? Okay. So identifying place. Well, what if you had a flat earth? And many people for many years thought the earth was flat. We know it's not. But they thought it was. But some people, there is still a society, I think it suggests, but the Flat Earth Society. There is an actual organization like that. I think it's sort of a joke, but it is. If we were flat, all you would need to know is how far to the right of the edge and how far down from the top. You would know exactly where you are. Okay? We don't live on a flat earth. Okay? We live on a spherical earth, which makes it a lot more difficult. So position on a flat surface, intersection of 2 straight lines, one vertical, one horizontal. Will not work well for a curved surface like the earth. So here we have to have a different approach. Okay? Now, those who get fired up about mathematics, there are cylindrical and spherical coordinate systems. We're kind of going to use something like a spherical coordinate system, but the math is not as complicated as the spherical coordinate. But that's basically what we're based on. Yeah. I'm sorry. It was a fun weekend, but it was a long weekend. I didn't personally, but we were involved with planning about 219 trees for the weekend. So I'm kind of beat. Okay.
You said planting?
Planting.
Really?
Yeah.
What kind of trees did you plant?
We planted white oaks, cherry bark oaks, and red maples. Second?
This for a big something, right?
Well, what it was, I grew up on a farm in Georgia, and my 2 brothers who still live on the farm, and sister too, who live on the farm, they're getting too old. None of the kids want to come back and farm, so we sold the cattle and we quit doing the grains, and so all the land we're planting in trees, almost all of it. So the part that's ours, we wanted not just pine trees, we wanted a few hardwoods too.
What's a good shade tree?
Okay. As far as, in my opinion, I love a mimosa. But mimosas are sort of messy because they have the beautiful, sweet-smelling pink flowers, but those flowers fall. And then they have those seed pods that form, and those seed pods fall. So they're sort of a messy tree, but I love a mimosa for good, deep shade. China berries make good shade trees too, but they have those berries which are sort of messy too. But as far as oaks go, we have 2 huge white oaks in our yard, and they're great shade trees. White oaks, yeah. They're very slow growing though. I've heard that I think it's called the sawtooth oak is a pretty fast growing oak. So there's lots of variety out there. All pretty good. All right.
Have you ever
Yeah.
planted a Virginia pine on your
What's that?
Have you ever planted some Virginia pines on your
We have planted Virginia pines before, but we sold the piece of land where they were, so I never knew what happened to them. No, I'm sorry, those were Mexican cypress, but I've seen Virginia pines planted too. Yeah. Sorry, I was thinking different. We planted them for Christmas trees, but we moved before they ever got big enough to be Christmas trees. So as far as I know, the next owners just let them grow. Okay, so here's how we use the globe, the poles, and the equator to determine place. This is the first step in it, okay? So the intersection of, oh yeah, this is what we had on the last. On a curve, on a sphere like we have, or a nearly sphere, the equator is at 0 degrees. And then they have what they call the parallels. And you can divide these, I wish they divided them by 15. 15 degrees, 30 degrees, 45 degrees, 60 degrees, to 90, 75 and 90. That would make more sense than 20, 40, 60, 80, 90. Okay? However you do it, these are the parallels. Okay? Now, each one of these parallels is a smaller circle than the original. This is the only one they call a great circle, the equator. If you're on the equator, you're at 0 degrees latitude, north or south. If you're above the equator, you're 20 degrees north or 40 degrees north or south, 20 degrees south. We're at 33 degrees, 23 minutes and 45 seconds north of the equator. So we're somewhere around in here. Okay? Okay? So those are the parallels. But then, you're just on some circle there. You don't know where on the circle you are. So we need another measure. Okay? All right, before we move. Okay? Well, okay, go back to this. Let's imagine you cut a wedge out of the earth. Let's not do it. Let's imagine you did. You'd be awfully hot right here. Okay, now, if you put a protractor in there, then this would be your 20 degrees, your 40 degrees, your 60 degrees, and the 90 degrees. I cut out the 80 here. That's how you measure degrees north. Project that outward to the surface, and you have these. If they're all 20 degrees apart, equal bands, so you get here in the 30 degrees there. But this is how we measure the first coordinate that you would have. Okay. And this, I believe, is I don't have my glasses on, so I'm having trouble reading. Antonio, got it. Thank you. I just had landed on you. Okay. All right. Now, so that gives you one measure. But just like if you had a flat sheet of paper, if all you knew is how far you are from the bottom of the page, you'd be anywhere along that line. Well, now you're anywhere along that circle. You need another measure. What? Ah, okay. This is Brianna, right? Okay. All right, we're slowly going to make a class here. Okay, we're still missing Asia, right? And Katie. And Kaylee. Okay. Now, here's the next measure you'll need. This time we're going east to west. Now, here we got a problem, folks. North-south, we have a north pole, we have a south pole, we have an equator. You can measure the angular distance between them. That makes sense. How are we going to measure around here? There's no poles, there's no fixed position on that. So someone had to come up with a fixed position. And when they were coming up with this, happened to be a time when Britain was queen of the ocean, right? Back in the height of the British Empire, their naval observatory was located at Greenwich, England. Greenwich, England is where we measure everything from east to west. That meridian that goes through Greenwich, England is 0 degrees. They call it the prime meridian. First, the one, only 0. Okay, 0 degrees. Okay, that goes north to south here. Okay, right through Greenwich, England. Now, just a dumb story here. My wife had professional meetings, I think either in Paris or in London, but she was going to visit both places while she was over there, and she decided to invite her niece to go with her, because she was like college age or something like that, and thought she would get a lot out of it. And it was summertime. I was teaching, so I couldn't go. Well, when Karen's mom heard about it, I want to go. So then she had to plan for her mom to go. And then Karen's sister found out about it. Well, I want to go and take my daughter, Michelle. So she wound up taking it. So she finally just canceled her meeting, didn't go to that, and just took them to England and Paris. And I think they went to England first. And they flew into London. They stayed in London, if my memory's right. And they took a day trip out to the Naval Observatory at Greenwich. They happened to be, they were dedicating a brand new facility out there, laboratory or something. And because they were, it was a Royal Naval Observatory, so therefore the Queen came to Christmas. They got to see the Queen. Okay? They didn't even know it. That wasn't part of their plans. They just lucked out and were there. Okay? Me, I would have gone to Westminster Abbey to see the tomb of Isaac Newton. That's more than okay. But anyway, so that's what they chose this by. 0 degrees, that's the prime meridian. There it is, prime meridian. The first. Everything else is measured from that. You turn to the east, and you're so many degrees east. Now here you go 0 to 90, you're just a quarter way around the Earth. Go all the way, halfway around, and you're at 180 degrees. Notice the north-south, 0 to 90 north, 0 to 90 south. That's your latitude. Your longitude, or your meridian, are 0 to 180 east, 0 to 180 west. We're over here around pretty close to 90 degrees west, that side. Okay. Now, that's the second measure. So if you know your latitude and you know your longitude, you know right where you are anywhere on the surface of the Earth. Okay. Everybody got it? So, the position you are on Earth is the intersection of the parallels, which are the north-south, and the meridians, which are east-west. That's defined with respect to the rotational axis. The parallels are your latitude, the circles that go up and down, and the meridians give you your longitude. Okay? So, parallels are always so many degrees, something always between 0 and 90, north, 0 and 90 south. Your meridians is so many 0 to 180 east, 0 to 180 west. That gives you your longitude. Okay. Now, in some locations, you will see them use pluses and minuses. Pluses are north, minuses south, pluses are east, and minuses are west. More common is you use the north, south, east, west direction indicators. Okay, here's that same figure we saw before of the parallels. These measure this is 20 degrees north latitude, 40 degrees north latitude, 60 degrees north latitude, 80 degrees north latitude, or the North Pole is 90 degrees north. We are at 33, 23, 45, right in there somewhere. You can go so many degrees south, down to 90 degrees at the South Pole. Okay. So that's your parallels are your latitude lines. Okay. How far north or south you are of the equator. How many degrees. Remember, one key feature of the North Star, always, its angle above the horizon is always your latitude line. We did that in the first lab. Okay, yeah.
I don't know if this is even related to this subject. I know since you said meridians, I was thinking about this city of Meridian, Mississippi.
Okay, I've often wondered that.
So
They're not right on any meridian. I don't know who gave it that name. Maybe at one time they thought they were and they were just wrong. I don't know. They're pretty close to 90 degrees, but they're not on it. Meridian, Mississippi, as you can visit here. There's 90 degrees, and it goes just about dead through the middle of Meridian, whereas Meridian, Mississippi is over here on the border. I think they probably thought they were on the 90-degree meridian, so they named it that. They were
Where's the meridian on the globe?
What's that?
Where's the meridian on the globe?
Okay, the meridia are always these. Here's the prime meridian through Greenwich, England. There it goes to that just east of London. That's the prime meridian. Here is 15 degrees west, so 30 degrees west. There's 15 degrees west, 45 degrees west. These are, all the meridians are great circles, because they all go through the North and South Pole. They get closer together here, further apart here, closer together here. The parallels, just want to make sure y'all are awake. There's only one great circle, that's the equator. The rest of them are getting smaller, but they're always the same distance apart. Okay? Meridian are closer at the poles and wider at the ends. Okay. Everybody got this now? Okay. So this again is the same thing we saw before. I don't know why they showed it again. That's your parallels or your latitude lines. Okay. Your longitude lines, this is similar to what we had before, starting at the prime meridian, which is the 0 degrees, goes to Greenwich, England, and then you go east 20, 40, 60, 80. We're west 20, 40, 60. We're over here close to 90. We're 80, oh goodness, 88, 89, something over here west one. Okay. You get both of those, you've got a crosshat exactly where you are. Okay. This is, if you cut the Earth in two, put a protractor down there, that would give you your longitude lines. Okay, you've seen those before. Now, back to our places, special parallels or latitude lines are climate related, which mean in the long run, they are very similar in weather patterns. Long run. Okay? Can't say day to day, but long run. And these are, and we've mentioned them before, your equator, which is typically the warmest part of the Earth, because that sometime during the year, the sun is directly over the equator twice. That's the only latitude line when it's over it twice in a year. That's the equator. At vernal equinox and at spring equinox, autumnal equinox and vernal equinox, both of those times the sun is directly overhead. Everywhere else in here, it's only once a year. And that would be the Tropic of, no, that's not quite right. On average, more closely to the equator. Tropic of Cancer, guess how many degrees north that is of the equator? Say again? I can't hear. 23.5 degrees. How far is Tropic of Capricorn? South of the equator. 23.5 degrees. How about the Arctic Circle?
It's all in the same.
It's 23.5 degrees south of the North Pole. So you take your 89.60 and subtract from that 23.30, and you get, goodness, I can't do that, 66.30, I think it is. Yeah, I think that's right. Okay. So yeah, that's, and Antarctic Circle too, 23.5 degrees from 90 degrees south. Those are your climate related, and this is what we call everything between the tropics is a tropical region. Everything between the tropic and the Arctic or Antarctic Circle, temperate region. And anything above or the Arctic Circle, below the Antarctic Circle, polar regions. Okay? Frigidly cold. And all that is determined by that same 23.5 degrees, the Earth's tilt. Okay. The highest you can get above the equator to have sun overhead, 23.5 degrees. Syene, Egypt. Remember we did that at June 21st, or the summer solstice. Sun is directly overhead there. That's on the Tropic of Cancer. Okay? On the Arctic Circle, that's the day, 24 hours of daylight. Okay? On the Antarctic Circle, 24 hours of darkness. Then in the winter solstice, the sun's directly overhead at 23.5 degrees south. That's the day you get 23 hours of sunlight on the Antarctica, on the Arctic Circle, and 23 hours of darkness on the Arctic Circle. All these are climate related. All right, how about time? Remember, it was place and time. We've done place, let's do time. The time standards depend on measuring, and by the way, y'all have to let me know when it's 3:15. How close are we?
3:30.
3:30? Y'all are supposed to stop me.
Well, that's all right. We just let you go on. We're gonna take a longer break.
No. That means shorter break. Okay. So measuring time, there's my mark right there. That's where we'll stop for today. Okay? Here, y'all let me just carry on. Y'all need a little break before we start the lab? Okay. I'm going to pause this then. All right. So, again, remember, what is the line, the imaginary line, between when you're facing due north and going directly overhead through your, what's that point up there called?
Let's see.
The what?
The zenith.
Zenith. Through the zenith to due south. What's that imaginary line called?
Meridian.
Your local meridian. So when the sun crosses your local meridian, we're said to be in transit, that's the highest point it'll be that day. That's your local noon. That's your local noon wherever you are. Someone a few miles to the east or west of you, be a few minutes or seconds before or after that. So that's your local noon. Now, the interval from noon on one day to noon on the next day, that's what we call a solar day. Why solar? Because it's based on the sun crossing your meridian. Okay? Now, most of the rest of this page, well, there's a few words that are important. Number one, now this came from, can't remember if it's Latin or Greek. Okay? I think that maybe it was Latin. Okay? Ante, A-N-T-E, means before. So before the sun reaches your meridian, that's A.M. Post-meridian, that's P.M. Okay? So anytime after it's crossed your meridian, that's P.M. Okay? Now, that goes down to the other end, where you don't see a meridian or anything. That would be midnight. So anything from midnight to noon is A.M., ante-meridian, and from noon to midnight is post-meridian, P.M. Yeah, Latin. Before the meridian or after the meridian. Now, they do some other, well, I figure, sort of silly things here. You can read that to your heart's content. Let's turn over to page 370. Okay? Let's get to the procedure here. Middle of the page. Part A. The solar day versus the sidereal day. Now, what do you think sidereal means? Second? It's relative to the stars. Now, the sun's a star, so why would the solar day be different from a sidereal day? We'll see. Okay?
You said 370?
Second?
370?
Yeah, 370. Okay, 370, part A in the middle. Okay? Now here's the deal. Because we are doing two things, we're spinning on our axis, always, okay? And we're also very slowly moving around the sun. So that means a solar day will be from one time when the sun's directly overhead to the next day when it's directly overhead, but we moved a little bit. We moved a little way, so a solar day is slightly different from a sidereal. A sidereal day would be pick a star at night, any old star at night, okay, and get the brightest one out there, Sirius, say, or something like that. And when it crosses your meridian, Sirius crosses your meridian, sun's that way over there. Okay, when Sirius crosses on one day to the next, hey, we're not going around Sirius. So therefore, that's going to be exactly one sidereal day, which is a little bit different because the solar day, we're not just spinning once, we are moving a little bit more. Okay? You can sit there. All right. So, it says first we will adopt a geocentric perspective as if we're the center of the universe. We consider the Earth to be motionless in the celestial sphere and the objects to revolve around us. Sounds like a teenager, doesn't it? Okay, never mind. Okay, then, let's do this. The sun moves how far around the ecliptic in a year? 360 degrees. It goes all the way around the ecliptic in 1 year. How many days does that take? 365. So that's almost 1 degree per day. Right? In fact, it's a little, almost 1 degree per day. Okay? This is on page 371, number 1. Therefore, the sun is about 1 degree east. Okay, now what they're talking about, let's just imagine that we start on the vernal equinox, March 21st. On March 22nd, since it's moved 1 degree along the ecliptic each day, approximately, then it's about 1 degree east of vernal equinox. Okay? So now, yes? Yes, is it 3:45? Boy, that flew by in a hurry, didn't it? Okay, here's my pen. All right. Bridget's still here. Brianna's still here. Jerome's still here. And Aisha never showed up today, did she? Okay. Jacob's still here. Oh, okay, here. Okay. Kaya, did we lose Kaya? I don't see her. Okay. Rakiria, she's not back yet, but she said she was going to take 7 minutes. Okay. Justin's still here. Sherlanda's still here. Tarsha's still here, telling me what time it is. Okay. Eric is still, well, he was here. Did we lose him? His stuff's still here, isn't it? Okay, we hope he'll be back. Zach is mostly here. Okay. Katie did not make it in today. Brandis has moved up in the world, but she's still here. Miss Lewis was here, but I imagine she'll be back. Antonio is still here. Just got here, but still here. Okay. David is here. Okay. Tiffany is still here. Kaylee didn't make it in today yet. Donald was here. And Shakaya is still here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 3, 4, 7, 8, 10, 12, 13. Got it. We'll see if the others make it back. Okay. So, where we left off before roll call, is page 371, number 1. Sun moves about 360 degrees in 365 days, so it moves about 1 degree per day. Therefore, the sun is 1 degree further east of where it was before, the day before. And Miss Lewis is here. Okay. Now, calculate how long you have to wait until, now here's the situation. Look at your labs. Here you were on spring equinox. The sun was sitting right on, the sun is always on the ecliptic, but where the ecliptic crosses the celestial equator, that's where the sun was that day. Okay? On your local meridian, that's your noon on that day. Now the next day, because we've rotated around the sun, or revolved around the sun a little bit, but made one complete rotation, that's where we were one complete rotation later, but the sun's over there. So the question is, how much further did the sun go there? Here's another way of looking at it. On vernal equinox, our noon was right there. One spin later, we were here, but you have to go a little bit further to get 1 day later, 1 solar day later. Okay? So what we have, calculate how long you have to wait after the situation in figure 48.1b so that the sun is on the meridian. So basically what we're doing, let me turn on my projector again. And if you can't see this, we'll turn off the lights. You can't see it now because the projector bulb is just coming on. But whoops, get my pen set up. Okay. Can you see it yet? No. Not yet. Go on and turn off the lights for now. We'll turn them back on in a minute. Both of them, yeah. See it a little better? Okay. We see the sun has moved about 1 degree in 1 day, right? Now, this is 1 day. How many hours is that? 1 degree in 24 hours. Okay? Now, wait, I probably shouldn't. Yeah, okay. Now, how many minutes is that? Multiply that by 60 minutes per hour, and you have 1440 minutes. Okay. Okay. Now, the question is, so that's 1 degree and 1440 minutes. Okay.
So let's see. What did you do now? I got a calculator. You got
Okay. Okay. Let's do it this way. Okay. 360 degrees would be do this every year. Okay. Okay.
24 hours. That's what
Yeah, 1 degree is 24 hours.
Okay, then you're gonna multiply that by 60 minutes, right?
Right?
That's gonna give you 1440.
Right.
Okay.
Okay. Now, someone just do this. Take 1440 and divide it by 360. I think I'm doing them. I've got it upside down, but let's try that. What do you get? Someone got a calculator?
He said,
4.
4. Okay. That's 4 minutes for every degree. Okay. So that's how long it takes. Okay. I knew I had it in there. I just had it upside down. Okay. It takes 4 minutes for it to move 1 degree. Okay. So that means, yeah, that's number 1. Calculate how long you have to wait after the situation in 1448, figure 48 1b, so the sun is on the meridian, and that's about 4 minutes. Okay. Now, so what we've just shown, they describe one way of showing that a solar day is a little bit longer than a sidereal day. A sidereal day is when that star is on your meridian. Because we're not moving around the star, we don't have to account for that little bit of extra time. Okay? Let's jump down to number 2. Figure 48.3. Okay? Now this is the one that drives me crazy. Okay? Here's 48.3. It shows the Earth over here, the Sun here. The Sun is eclipsing Leo, the constellation Leo, the lion. Now that actually almost looks like it could be a lion. Could be an aardvark or something too, but they chose a lion. Okay? Now, read what it says here. 48.3 depicts the sun's apparent motion along the ecliptic, where the zodiacal constellations are found, in a heliocentric perspective. As the Earth orbits the sun, the line of sight of the sun toward the background stars also moves. For example, the diagram shows the sun in Leo. A month later, it would move enough so Virgo lies behind the sun. And there's Virgo right there. 1 month later, we'd be over here. Virgo would be behind the sun. Does anyone see a question there? No, there is no question. So number 2, since there's no question, it has no answer. Okay? So Donald is back, and so is Mercuria, if I can find it. There you are. Okay. Kaya has not made it back. And did Eric make it back? Not yet. Okay. So most everybody's made it back. So number 2, bottom of page 371, there's no question, there's no answer. So you can leave that blank with impunity. No charge. Okay? Let's go over here to part A, the analemma. Now these are details of the sun's motion. Now, here's where we get the word from. The 3-coordinate plot, that's a little unusual to have 3-coordinate plot. The word analemma from the Latin sundial. Okay? Now that's not the sundial I'm used to seeing, where you have something up here and it has the hours of the day here and it tells you the hour of the day. This is a bigger analemma. Here it is. And when they say 3-coordinate plot, horizontally you're measuring time in minutes. In the center is 0, and to the right are 2 minutes, 4 minutes, 6 minutes, up to 14 or 15, 16 minutes. To the left, 2 minutes, 4 minutes, 6 minutes, up to 18 to 20 minutes. Okay? So there's one measure, time in minutes. Then you have declination of the sun, north and south. How far up in south, north and south will it go? Declination of the sun. Help me. How far? North and south will the sun go?
23.
23 and a half degrees, and sure enough, this goes up to 24, but it doesn't ever reach 24. It goes down to 24, but never reaches 24. So it goes up to 23 and a half, down to 23 and a half. Okay? So that's the second plot on here. The third plot is the day of the year. And if you'll notice here along the analemma, this figure 8 you got, where do you want to start? Name a day of the year. December what? December the 1st? December 1st is right here. Okay? That first, you see November 30th here, then the next little block is December 1st, 2nd, 3rd, 4th, 5th, right there. 6th, 7th, 8th, 9th, 10th, right there. 11th, 12th, 13th, 15th. So the day of the year is measured along here. So there's your three dimensions. Time in minutes, declination of the sun, and day of the year. Now going straight up the middle is clock noon. So the minutes are measured before or after clock noon, and your declination is north or south of the equator, celestial equator. Okay? So there's your analemma. That means sundial in Latin. We'll run into another word that also means sundial in Latin, but we're not going to mess with it now. Okay. Now, what causes the changes here? Well, part of this is the tilt of the Earth's axis. That gets the sun up to 23.5 degrees north and 23.5 degrees south. So the tilt of the axis is involved. Another part is the fact that sometimes we're further from the sun and we're going slower, closer to the sun, and we're going faster. Okay? Well, up here in July, around July, I don't know, sometime here we're at our farthest distance from the sun, and so we're going more slowly. So you see how close together the days are there. Down here, when we're closer to the sun, we're moving faster, and you see the days are a little bit further apart. So that makes us wider in the bottom half of the 8 and narrower at the top half of the 8. Okay. Now, when is the sun on the celestial equator?
During the eclipse.
Not eclipse? Okay, so sun's always on the ecliptic.
Okay.
When does the ecliptic cross the celestial equator?
On March 21st in June.
Equinoxes. And sure enough, September 21st or so, actually more like the 24th or 23rd or 22nd, 23rd, and March 21st, 22nd. Sure enough, there the sun is right there, smack down on the equator, celestial equator. So, that gives why we have this variation. So if you turn over to page 376, okay, number 3, briefly describe the effect of the shape of the analemma, that's that figure 8 we saw back on the other page, if the ecliptic equator angle were to increase. In other words, if we go from 23.5 degrees to say 24 or 25 degrees, how would that change the analemma? Say again?
I'm lost.
Okay. If the tilt of the Earth were a little bit greater, like 24 or 25 degrees, how would that change the analemma here?
Would you speed it up or slow it down?
Okay, we're not talking about speed,
Okay.
the shape.
Oh. Look like a tree center.
It would string it out longer vertically. Because then you would be, here's 23.5 degrees, north and 23.5 degrees south. If it was 24, it would be there and there. 25, it would be there and there. You know, it would stretch it vertically.
So that means at the top it'll be bigger.
It'll be greater, and at the bottom greater. So it stretches it vertically. Okay? That's number 3. Briefly describe the effect of the shape on the shape of the analemma if the ecliptic equator angle were to increase.
And the answer would be it stretches.
Stretches it vertically,
Oh,
making the 8 a longer 8. Stretches it vertically. Okay? Says, obtain from your instructor the latitude of your location and fill it in below. Anyone remember it? 33 degrees, 23 minutes, 45 seconds. 33 degrees, 23 minutes, 45 seconds. Put that on number 4.
Wait, can you say it one more time?
Okay, number 4. 33 degrees, 23 minutes, 45 seconds.
Dr. Fowler, you said for number 3 it stretches it horizontal.
No, it stretches it vertically. Top to bottom. Stretches.
Yeah, 45 seconds.
And then the latitude is 33 degrees, 23 minutes, 45 seconds.
So you dividing that?
We're not doing anything yet, okay?
Okay.
Determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Okay? So, let me clear this off the screen. All right. Now I'm going to draw our little globe down here. And here we are standing on top of it at 33 degrees, 23 minutes, 45 seconds. Okay? Here is our horizon. Oops, that's not a very good horizon. Okay, it goes up here. What's that point directly overhead? Our zenith up here. One of those is really poor. Let's see if I can pick the better one. That wasn't very good. Let me just erase it and do again. Yuck. Okay, let me try that again. That's still not very good, but it's better than the last one. Okay. Determine the altitude over the southern horizon. This is the northern horizon. This is the southern horizon. Okay. Of the intersection of the celestial equator and your local meridian. That's your local meridian. There's your zenith. Okay. The celestial equator will be at 33 degrees, 23 minutes, 45 seconds. Okay, that's that angle there. This is celestial equator. So now we want to know what's that angle. How are we going to get it?
You gotta subtract 90 degrees.
Yes, but instead of 90, we'll use 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds, 1 degree, that makes it 60 minutes. 60 seconds is 1 minute. That would make it 60 minutes, and 60 minutes is 1 degree. That makes it 90 degrees. Subtract from that the 33 degrees, 23 minutes, 45 seconds. I'm sorry? 89. Okay. Do the subtraction. What do you get?
89 degrees.
Do the subtraction. It's 89 degrees, 59 minutes, 60 seconds. That's 90 degrees. Subtract from that 33, 23, 45. What do you get? Come on, it's not that hard of math. 50, 56 degrees, 36 minutes, 15 seconds. Perfect. That's the second part of 4. Determine the altitude over the southern horizon of the celestial equator. That's it. Okay? And your local meridian. Now, what we're going to do now, folks, and this may be a good time to turn back on the lights. I don't know if it is or not. Tell me if it's wrong. Okay? David, can I get you to turn on the lights again? All right. Now, says use an analemma in figure 48.4 and your answer in step 4 above, okay, to fill in the table 48.1. And this did say 47.1, I changed it to 48.1. The latitude of Altegard, Norway, by the way, will be plus 70. We'll do that in a minute. Let's do declination of the sun on February 15th. Can we get that from the analemma? All right, tie us back. Okay. Oh, and I'm missing Eric. Come in. He came in. Okay. Did everybody who's here get the lab? Here, you can use that one. They Eric, did you get a lab? Okay. Everybody got one. Okay. Okay, we're looking at the analemma on page 374. Okay? Now, can you tell from that what the declination of the sun is on February 15th?
13.
February 15th.
Yeah,
How do you read that?
Okay.
February 15th.
All right. You found February over here? Okay. February 15th is right there near the F and the E of February, right? Okay. Come across that line horizontally until you reach the declination of the sun. What is it?
13.
13 degrees
South.
south. Okay. So you can either put 13 degrees south or minus 13. I don't care which. 13 degrees south. That's what goes in the first blank there. Okay, let's go down to June 21st. Can we find the declination of the sun then? Wait, let's just stop. Okay? So we found declination of the sun on February the 15th. Okay? That was, say again what it was? 13 degrees south. So that's 13 degrees south of the celestial equator. Well, there's the celestial equator, so the sun's going to be something like this on 15 February. Okay? Now what it's asking for on the second block there, I've got to find my page again, flipping pages back and forth. What is the noon altitude of the sun at our location on February 15th? Our celestial equator is there. Subtract from it 13 degrees south, right? So subtract 13 degrees from this. And what do you get?
56.
From 56. 43 degrees, 36 minutes, 15 seconds. 43 degrees, 36 minutes, 15 seconds. That's the middle block, noon altitude of the sun at your location. Okay. Now let's go down to June 21st. Go to the analemma and find June 21st and what you see the declination of the sun to be.
So you see the noon altitude of the sun at your location?
At our location, where we live.
Okay.
And it is 13 degrees south of celestial equator. So that would be 13 degrees south of the celestial equator, which is there. Subtract 13 from that. 43, 36, 15.
Need a new altitude of the sun at Altagar.
Yeah. Okay, we're not going to do Altagar yet. We're going to stay on our location, do the table there, then we'll draw a new one for Altagar. Okay. All right, so let's do declination of the sun on June 21st. What's that? It's what? 23.5 degrees north, right? So that means you add 23.5 degrees to our, to where we are here. So 23.5 degrees would be something like this. 23 degrees, 30 minutes. So add that to our 56, 36, 15, right? 56 degrees, 36 minutes, 15 seconds. Add to that 23 degrees, 30 minutes. Now let's do this one left to right. Say again? Okay. Here's the celestial equator. That's at 56 degrees, 36 minutes, 15 seconds. Okay. On June 21st, we're up there at 23.5 degrees beyond the celestial equator, above the celestial equator. So that means you add the 23.5 degrees to your 56, 36, 15. That's what I'm doing here. This is adding. Okay? Now, let's go left to right, right to left on this one. 15 seconds. When you add these two, what do you get? 66 minutes. Well, 60 minutes is 1 degree. So that'll be 6 minutes, add a degree here, and that gives you 80. 80 degrees, 6 minutes and 15 seconds. Okay? So there we are at June 21st. So the noon altitude at our location on June 21st, the declination of the sun was 2330 north plus, and noon altitude of the sun at our location would be 80 degrees, 6 minutes, and 15 seconds. All right, everybody got it? Now let's go to October 15th. Okay, we found that on the NLM. You see it? 8 degrees south. So 8 degrees south would be not quite as far as 13 degrees south. That'd be like this. So this is 8 degrees south. Okay? You subtract that from your 56 degrees, 36 minutes, 15 seconds. And subtract 8 degrees from that. And what does that give you? 48 degrees, 36 minutes, 15 seconds. So that would be the noon altitude of the sun on October, 15th? What page is so much here? Okay, how about December 22nd? What's the declination of the sun? Say again? Not quite 24. It never gets to 24. 23.5. It's awfully close to the winter solstice. So that would be minus 23.5. So I'm going to erase some stuff if that's okay, because it's getting awfully crowded. Okay, let's erase this. So I don't want to erase that. Okay, we'll erase this and that. Okay. And I think I can draw in the rest of it. Okay. subtract from the celestial equator 23 degrees and 30 seconds. Okay, I could erase this line here.
56 degrees and 36 minutes.
What's that again?
You subtracted 56 from 23.
No, 23:30 from 56. 23 degrees, 30 minutes. We're subtracting that from 56. And what do we have?
30 degrees. 30 degrees. 6 minutes.
Okay, 33 degrees, 6 minutes, 15 seconds. So that's the noon altitude of the sun at our location on December the 22nd. Barely a third of the way up the sky. Whereas on June the 21st, it was almost directly overhead, less than 10 degrees from directly overhead,
What was that?
80 degrees. Huh?
What's the noon altitude of the sun on the second? I mean, on the one that says December 22nd.
December 22nd, that's what we just did. The sun is 23.5 degrees south of the celestial equator, so you subtract that from the altitude of that.
What happened to October 15th? That goes back.
Okay, October 15th, that was 8 degrees below. And that was the one we subtracted here.
48 or 36.
Right. Everybody see what's happening?
That's the noon altitude. You're talking about 48, 36, 15 seconds.
That's on October the whatever it was, 8th.
36.
No, October 15th.
And October 15th was declination of the sun. 8 degrees. And December was what? 23.
23.5 degrees, declination of the sun. All right, you thought we were cold here this morning? We're going to Altegard, Norway.
Okay.
Okay, where's that? Yeah, that's inside the Arctic Circle. The latitude is 70 degrees north. Okay, so I'm going to erase most of this. So everybody got every bit we needed for our location. The first two blanks, right? Okay. All right. The latitude of Altegard, Norway is 70 degrees. So that makes it way down there. They're 70 degrees north. So that means we're down here. Here's our 70 degrees north. Okay? That's the celestial equator, because this is the equator. Celestial equator is down there. So what's the noon altitude of the celestial equator from the south horizon? If that's 70, this would be We're going to do Altegard, Norway, but we have to position the celestial equator first. 20 degrees. Okay, 20 degrees north of the the southern horizon. That's where the celestial equator is. So February 15th, what was its declination? You've got it written down there. 13 degrees. Subtract 13 degrees from that, and what do you get? 7, right? 13 from 20 is 7. So the noon altitude of the sun, Altegard, Norway, on February 15th, 7 degrees, barely above the horizon. Okay? Just 7 degrees above the horizon. Okay? Everybody see it? Okay, June 21st, where is the declination of the sun? 23.5 degrees. So you add the 23.5, I'm sorry, I did that wrong. Okay, you add the 23.5 degrees to the celestial equator. How far above the southern horizon is the sun then? And this is June 21st. What would that be? Say again? 43.5 degrees. 43 degrees, 30 minutes, or 43.5 degrees. Perfect. Noon altitude of the sun at Altegard, Norway. Okay? October 15th. That was 8 degrees south, wasn't it? Okay, subtract 8 degrees from 20 degrees. 12. So noon altitude of the sun on October 15th was 12 degrees above the horizon. Not very high. Yes.
Okay.
I'm sorry?
I'm not sorry. What are you subtracting?
Okay. You found the declination of the sun, didn't you?
Yes.
On those 4 dates. Okay? Some of those were pluses or north, and most of them were minuses south, right? You've got the celestial horizon, celestial equator here at 20 degrees north. Now, when the sun is below the celestial equator, like on, what was this date? February 15th. It was 13 degrees below the celestial equator. So you subtract 13 from 20 and you get 7 degrees. On June 21st, the sun was 23.5 degrees above the celestial equator. Above it, that means you add it. 20 and 23 is 43 degrees, 30 minutes. Right? October 15th, you were down here at 8 degrees. I didn't write it in yet. I was in the process of doing it when I saw a hand go up. You subtract that 8 degrees from 20 degrees, and what do you get? 12 degrees. Okay? And how about the next one?
Is that 12 degrees south?
What's that?
Is that 12 degrees south?
That's 12 degrees south. Isn't that what you got on the declination of the sun, October 15th? So that means you subtract the 12 degrees from your horizon, altitude of the celestial equator. What was it on December 22nd? 23.5 degrees. So what was it at Altegard, Norway?
23.5.
You subtract 23.5 from 20, and what do you get? Yeah, you're below the horizon. You never see the sun on December 22nd at Altegard, Norway. You're above the Arctic Circle, no sun that day. None. So you can either say minus 3 degrees, 3.5 degrees, or minus 3 degrees, 30 minutes, or you can just say it never rises. Okay? Because you're above this Arctic Circle. And on the winter solstice, it doesn't happen. All right. Now we go back in history. Okay? Good old Rip Van Winkle. Does anyone remember him? Okay, good old dude, wasn't he? What was he famous for? Snoring and clap. No, that wasn't it. What did he do? He took a long nap. Okay? Rip Van Winkle awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. The passerby quickly responds and rapidly moves away. I wonder why. If he'd been sleeping 20 years, he's pretty ripe, don't you think? Okay. Probably not too attractive either, okay? So, realizing a 20-year snooze might be a world record, he thinks he should pin down the date as well as the year. He moves out from under the tree where he slept for 20 years and measures the altitude of the sun when it crossed his meridian. Now, boy, wasn't he clever to have that when he woke up. What's that?
I gotta get this straight. This man slept underneath the tree for 20 years.
That's what it says here. I'm just making this up. Okay.
That's not realistic.
No.
No, it isn't. Okay.
He might as well be part of the tree.
What's that?
He might as well be part of the tree.
Yeah, you would think. And I don't even want to ask about bodily function, so let's move on. Okay. All right. He measures the altitude of the sun when it crosses his meridian and finds it 44 degrees above the southern horizon. So 44 degrees, let me get my pen set up, is going to be something like that. 44 degrees above the southern horizon. That's the sun when at noon on that day. Okay? He knows that the latitude of his chosen spot on the Hudson River in New York is 42 degrees. So let me go in and change my little globe here to 42 degrees north. Something about like that. So there's, it's too much. Let me go back and change it. 42 degrees. That's probably too little, but we'll just call this 42 degrees. Now that's from the equator, celestial equator, to his zenith. That's going to be 42 degrees. From the celestial equator to his zenith. Right? 42 degrees. Mine doesn't look anywhere close. Let me clean that up just a little bit. Okay, something like that. All right. Now, from this, what do we need to determine? Here's celestial equator, there's the sun. What we need to know is what is the distance from celestial equator to the sun? That has a name, that angle. Celestial equator to the sun. What was the first column in our last table? Say again? Declination. That's how far the sun is either above or below, which is it here? We are below. No, there's celestial equator, there's the sun. 44 degrees here, 42 degrees there. What's the difference? 42 and 44 add up to 86. So what's the distance here between that and 90?
4 degrees.
4 degrees. So the declination of the sun is 4 degrees south of the celestial equator, right?
And the first part of number 6, right?
Say that again.
The first part of number 6, right?
The first part of number 6. That's what we're working on.
Oh.
So the question is, on what two possible dates could Rip Van Winkle have awakened? So where will we go to find that out? Our good old, what's that called? Analemma. Go to your analemma and find 4 degrees south of the celestial equator. Okay? And go across here and find the date. First date was? Anyone see it?
October 5th.
And I would go the other way. 4th. See, there's 5, 6, 5, 10, 15. So it's one day before. That's October 4th. Or go on across from there. I can't read because I don't have my glasses on. And what date is that?
March 13th.
March the... Say again? No, it's 15, 20, so it's not between 15 and 20. 4 degrees is below 15, so it's between 10 and 15. What would that be? Well, maybe 12. Okay? Let's just say 12. March the 12th. Okay, those are the two possible dates. October what? October 4th or March the 12th. Okay? Y'all got them written down? Okay. So that's the first question on number 6. The second question says, he notices that buds are appearing on the tree he slept under. So what was the date of his awakening? That would be the March one. Okay? So either circle that one or write it down again or something. Okay? Got it? All right. As we saw previously, the analemma graphs the daily differences between clock noon and apparent noon when the sun crosses the meridian. As an example, now here's the example, middle of page 377. Check the analemma in figure, they got it all wrong, 48.4, to see that on October 15th, the sun will cross the meridian, October 14th, or what was it? 15th. October 15th, it'll cross the meridian, go up from the 15th, go up, straight up. That would be 11 minutes. No, it says 14 minutes. So I got the right date. I don't have my glasses on. October 15th. Oh, I was on the wrong day. I was on October 5th. October 15th. Go straight up, and you see it's 14 minutes before clock noon. So over here on the analemma, to the left of 0 is before clock noon. To the right of 0 is after clock noon. Got it? Okay. So that gives us where we are. So let's go down and do number 7. For the dates given in the table, use the analemma in figure 48.3, 48.4 I think it is, to determine. Now the first thing you're going to do is write in one of these two words, before or after. That's all. That first column, the middle column, all you write there is before or after. Then in the right-hand column of that table 48.2, you'll write how many minutes. Okay? So let's find January 10th. January 10th. Anyone found it yet? It's after, so the first block is an after. Does everybody see that? Okay? January 10th goes straight up from there. Boy, you can't get much further, can you? How many minutes? Say again?
Say about 8 minutes.
It looked to me more like 7, wasn't it? Did y'all get 7 minutes? Okay. Amount of time before or after clock noon, 7 minutes. You already said after, right? So it's 7 minutes after. Okay. February 15th. It's after again. Go straight up from February 15th, and what you get? 14 minutes. Everybody got it? After 14 minutes. Huh?
So 14 minutes is the answer for that one, right?
Okay. Did you find it? Where'd you take it? Where'd you take it? Right there. January 10th. On January 10th. That's it right there. You go up here. You're on the after side. This is before, this is after. Right? No. Okay? Right here. Okay? The unlimited should, I'm sorry. As we saw before, as an example, check, see that on October 15th, that's when they tell them. On October 15th. October 15th. Right there. There we go. That's straight up from there. You see there's 14 minutes.
Okay, so
See that?
minutes up top.
Yeah, right. And read this, and it says up right here. As an example, on October 15th, the sun will cross the meridian 14 minutes. You see the 14 minutes before. So this side is before, that side is after. That is after. And then read the number of minutes here. And then these are before here. So January, what was it, 10th? Yeah, January 10th is down there. Is that on the board before or the after side? After, okay, and then go up here. And how many minutes? 7 minutes, you got it. Okay? Do it for the next one too. Okay, everybody got February 15th? After and 14 minutes. How about April 15th? Next day! Don't we love it? Okay? Okay, what do you got? You said after?
April 15th was what now?
April 15th. Did someone say after?
Yeah.
How much after? I'd say less than a minute.
Yeah.
You see it? April 15th? Right down in there? Almost on it. So it's after, but just the number of seconds after. Not minutes.
So what do you put?
Less than a minute. I would put less than 1 minute. After, less than a minute.
What about me?
Second?
Minute good enough.
I'd say less than a minute. You got room. Don't be lazy. Okay. July 30th. July 30th. After, you're right. How much after?
It's like 6.5.
6 or 7.
Yeah, 6.5 minutes, 6 minutes, I believe. Yeah, something like that. Everybody see it? Yeah or no?
What?
Second?
6 minutes.
I can't hear it.
After and what?
Well, what did you find? Did you find July 30th?
6 minutes after.
It's after? How many minutes after?
6.
About 6. All right. Okay. Then September 1st.
After.
So
Okay.
both sides are 6 minutes after.
Wait, is that
The amount
after?
of time before and after popping in the next column.
September 1st?
It's September 15th.
After about.
Yeah, it is after.
I put less than.
I'm trying to even find.
It's like exactly where it comes.
Okay. So put like me.
But what now?
Okay. 5th, 4th, 3rd, 2nd. I think it's barely after, but less than a minute.
So what you call it, noon?
I would say after, but less than a minute.
Okay.
Okay? How about October 30th?
Before.
Before, we finally got a before. How much before?
16.
Really? Oh yeah, I'm sorry, I went the wrong way. Yeah, that looks right.
We're on September 1st.
I thought they were on October 30th. I didn't even see it September. Oh, you said September 1st?
No, that's the A.
Okay, September 1st was when? After, but less than 1 minute.
Oh, that one was after this.
Right?
I missed that, guys. Hold on now. You said
October
October 30th.
Is it after?
October 30th. Before.
It's July 30th.
I
is
got
after.
8.
Say again?
So there's 1, 2, 3, 4, 5 after 24.
That's it.
You said October 15th, right?
All right.
October 30th.
October 30th, so that's way.
Yeah. About as far to the left as you can go in the bottom quadrant.
Okay, so what do you go?
Not quite, close.
You're gonna go up to the minutes, right? So it'd be 10 minutes, wouldn't it?
Everybody got it?
Hold on, just one
Okay.
second, we're trying to get this problem solved.
Okay.
So on October 30th.
Found it. It's on the before after side.
Okay, so that's here. 60 minutes.
Got it? Okay. Flip one more page. Page you've been dreading.
And this is before.
Okay.
I was putting it wrong, okay.
Okay. Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian, our local meridian, on the dates in the table below. Okay? So we got to go back to our local meridian. Okay? All right. So I think we're going to have to change my picture again. Can you see it okay with the lights on, or would you rather have them off? Okay. Now, our local, we are at 33 degrees, 23 minutes, 45 seconds. Okay? That will be about there. That may be too much, but we'll go with it. 33 degrees, 23 minutes, 45 seconds. Okay? That leaves this to be what? Anyone remember? You can flip back a page or two and see it.
Now, you said, what was the question?
Okay, we're doing number 8, top of page 378.
Okay.
Determine the altitude over the southern horizon of the actual sun and the time it crosses your local meridian on the dates of the table below. Okay? So this is the celestial equator here. Does anyone remember its altitude? 56, wasn't it? 56 degrees. Say again? 36 minutes and 15 seconds. That was on the previous page, 376. Okay. So, we need to determine the altitude over the southern horizon of the sun, actual sun, and the time it crosses our local meridian on the dates in the table below. So on May 15th, what does the analemma give us about the sun? May 15th, wasn't it? Yeah. Anyone find May 15th? There we go.
Is it 19 degrees?
19 degrees north of the celestial equator. So that's 19. My pen's not writing. Now the pen's gone off. Now it's going back. Now it's in the slideshow. I don't know what's going on here. Yuck. Okay, that's 19 degrees north of the celestial equator, right? Can't get my pen back. There it is. Okay, 19 degrees north. So how far would that be above the celestial equator? Say again?
I think it's 75 degrees.
You got it. 75 degrees. So that's what you put altitude of the sun. 75 degrees, 36 minutes, 15 seconds. Does everybody see that? You add the 15 or 19 to the 56. 20 to 56 would be 76, so 19 would be 75. 75 degrees, 36 minutes, 15 seconds. Everybody see that? Okay.
That's the altitude of the sun.
That's the altitude of the sun above the southern horizon on noon. Okay? Let's do the time when it crosses the meridian. What was that? 15 May, was it? Yeah. 15 May. What time? Are we before or after?
Before.
We're before clock noon. How many minutes before? Say again? 4 minutes before clock noon. So what time would that be? 11:56 a.m. or p.m.? A.m. A.m. Ante-meridian, before meridian. Did everybody get that?
How did you get that?
Say again?
How did you get that again?
Okay. Did you find May 15th on the analemma? Okay. Are you on the before side or the after side? Before side. How many minutes before? Say again? 4 minutes. And what's 4 minutes before clock noon? Say again? 11:56 a.m. or p.m.? A.m. Got it. Okay. Does that make sense?
Yep.
Okay. Let's go to June 15th. Okay, first we got to figure out where the sun is, our altitude. What is the declination of the sun? 23 degrees. So there will be 23 degrees above the celestial equator. So how far would that be? What would the altitude be? The 23 added to the 56 would give us 79 degrees, 36 minutes, 15 seconds. Right? And then the next question, what time would it cross it? Say again? Noon, on the nose. So 12 o'clock noon. Did everybody see that? 0 degrees before or after. 0 minutes before or after. Okay? 12 noon. That's June 15th. November 4th. First, what's the declination of the sun on November 4th?
16 degrees.
It's, did you say 15 degrees?
Say that. Yeah.
Is that what you said? I can't hear well. 15 degrees?
15 degrees.
15 degrees. Which way? North or south?
North.
Really?
That's west. I apologize. That's west.
No, we're not east or west. We're north or south?
South.
South. Okay. So we're below the celestial equator by 15 degrees. Right? So what do we do with that 15 degrees? Subtract it from 56. And what does that give you? 41 degrees, 36 minutes, 15 seconds. Do you see that? Okay. What time will it cross? 15 seconds. 50. You see, you're subtracting the 15 degrees from this. That would be 41 degrees, 36 minutes, 15 seconds. You don't have any fractions there. Okay. What time was it? I've forgotten what day it was. November 4th.
4.
November 4th. Where is it? There it is. November, was that it? November 4th. Looks like 16 minutes. Is that on the before or after side? Before. What's 16 minutes before clock noon? 11:44 a.m. or p.m.? A.m. 11:44 a.m. Excuse me. Did everybody see that? Okay. Is this making sense? Okay, December 25th, Christmas Day. Christmas Day. What do you reckon the declination of the sun is on Christmas Day? I don't think it ever reaches 24 degrees, does it? 23 and a half degrees. So that'll be 23 and a half degrees above or below?
Below.
Below, okay. So this is 23 degrees, 30 seconds below. 30 seconds below. So subtract 23 degrees, 30 seconds. Minutes. Minutes. I said seconds, but it's minutes. What would that give you? 33 degrees, 6 minutes, 15 seconds on December 25th, Christmas Day. And what time does the sun cross it? Say again? 12 noon again. You got it. Does that make sense? Okay? Oh, tons of them. No, okay. No, you'd have to have all this stuff. You need to know basically what an analemma is. You know, you have to know things like what influences that, the tilt of the earth, the speed that the the earth is traveling around the sun, that kind of stuff, you know. Okay. What's that?
Based on the PowerPoint.
Based on what?
Based on the PowerPoint.
The PowerPoints, yes, yeah, right. Okay, got it. Yeah. Okay. I'm going to get out of this. Anyone need this up here any longer? This. Nobody needs this any longer? Okay, I'll discard it. And we're at 4:55. So if anyone does want to take their second test or their first test, we got time. You can have up to 20 minutes to work on a formula equation sheet if you want to, because you can have one for every test, including this one. This is Chapter 15 test. Huh? Which one, first or second? First? Okay. So if you need to get started now, you can. If you want to take a few minutes to do a formula equation sheet. And by the way, she left. I was going to tell Bridget. Does anyone know Bridget? She sat back there? Okay. Well, next time tell her she can always, if she doesn't listen to the videos, she can find out, you can have a formula equation sheet for every test. Did you know that too?
No, I just found out, so I can do it for Friday when I take my I'm gonna take 14.
Yeah, you do a formula equation sheet.
And I'm turning these my
Labs.
labs, so I just see on Thursday, and then I'm taking my test on Friday. I'm gonna be sure to remember.
Okay.
I'm about to go now.
Okay. Now, before we start losing people, let me get this. Okay. On Thursday, we will pick up on Chapter 16, where we left off today. That was on page 415 if you got the book, Measuring Time. We should be able to finish the chapter easily within 2.5 hours. So my guess is what we'll do is finish the chapter and probably start chapter 17. Then with 2 hours left, which will be 3:45, I'll give you the lab for chapter 16. Now the chapter 16 lab is a little bit different from any other lab you'll do. Most of the time on Thursday, we'll spend telling you how to do the little bit of the lab. And what you're going to be doing is observing the moon for something like 2 weeks. Okay? So, we'll talk about that. That'll be the first part we talk about. Then we'll actually do some lab work like we did in class the last 2 labs. Be a little bit easier. I think you'll find it pretty much fun to do, like all this was, right? Say yes. Okay. And then we'll finish up that lab. It probably won't take us 2 hours in lab, but guess what? You're going to have to do a little bit of time for every other day for the next 2 weeks to do the rest of the lab. So that's what we'll be. 2.5 hours of class, chapter 16 and probably into 17. And then the 2 hours lab, we probably won't do a full 2-hour lab, but the rest of the lab you'll be doing at home in the evening or in the morning, depending on whether you're an evening person or a morning person. You get to choose. Okay? So, all who are going to stay and take either test 1 or test 2, or both, you got time. If you're going to take a test, I'd suggest you have a formula and equation sheet. That's up to you, though, and then we'll move on from there.
We don't have a lot of formulas on there.
No, not really. There's not many formulas in the chapter. So, I just say, I use that term for it because I say it in every class. Math class and, yeah. Yeah. So it's whatever you want to write down on a piece of paper. Okay? So, how many of you are going to be taking test 1?
I am.
Okay, 1 I hear. Yes, sir. Thank you. Thank you. What's that? Okay, sure. If you need a little break, take a break. You got plenty of time. Either or both tests. Okay. So I heard 1 test 1.
How about test 2?
Okay, any other test 1?
Test 1 hard? I ain't prepared for that.
Test 1?
Oh, you need
Any other test 1?
That was my book.
What's that? If you're through with the lab, I'll take it. Now, give me plenty of grade. Thank you very much. All right. If there's no questions, I'm going to go and shut down the recording so it'll get loaded sooner.